Good afternoon to you.
By the time we wait, Dr. Deepak, if you want to check your presentation, so you can just try to clear and then see if everything
Okay, I'll
works.
just try to.
Because we are waiting 10 minutes, we'll start.
Okay, maybe, yeah, it's a good idea.
Yeah. Also, Dr. Carla is also here, right? So, Dr. Sharma?
I saw him somewhere.
Okay. If you want to check it up, also that can be possible. We can do that.
Yeah, I've just shared my screen. Is it visible?
Yes.
Okay, all good. Let me just put it in full screen mode once, just to be sure. Is it fine?
Not full screen is not coming.
Okay, so okay, let me do one thing. How about now?
Just perfect.
Yeah?
Yes.
Okay, great.
Yep.
All good then.
Dr. Shamal, can we start? It's 1:35. So
Okay.
let people come in. So maybe you can start.
Yeah.
Thank you so
Just
much.
a brief introduction before we start. I would like to welcome everyone, saying good morning to Italy and good afternoon to India and good day to all that are somewhere else, because I know some of the crowd is watching from abroad. I would like to thank, first of all, the participants. Yesterday, we had a very wide attendance with nice discussion. And I would like to remark for today that you have to feel free to ask any question, because this workshop is intended to share ideas, to share experiences. So the questions at the end of the talk are very important. So keep in mind that no stupid questions exist, especially if you are not very well into a given topic and you don't know something. You just have to ask and you will learn the answer. The speakers will be very happy to answer any question. I also would like to thank again all the speakers from yesterday. During the opening ceremony, Indian and Italian guests highlighted some ideas and opportunities to strengthen the cooperation between our institution, University of Florence, and Indian Institute of Technology Indore, and more in general, the cooperation between our countries. On top of that, I would like to remark that we had very interesting talks that highlighted a huge experience on and a huge amount of past works. So I'm sure today's talks will be at the same level or even better. So before we start, I have two service communication for all the Italians that PhD students that already started to ask me if you need a certificate of attendance, we will send it to you next week. Just wait a week or so, and you will get it by email with the email you register to this workshop. While concerning another point, very briefly, I would like to remind you again that University of Florence is organizing the 6th World Landslide Forum, a very important congress that will take place next November in Florence, Italy. So we all invite you to join the workshop and to send your works to the scientific session. Abstract submission is open till the end of this month, so you have plenty of time to pick up your session and to submit your work. I remind you that we are organizing jointly also a session on early warning systems. It's the session number 2.12. Check it out and submit your works. So that said, I think we can start today's scientific session. The first speaker is Dr. Ritesh Kumar, which is currently working as an assistant professor in the Department of Earthquake Engineering at EIT Roorkee. He's also affiliated as an Energy for the Future Fellow with Imperial College London, UK. Dr. Kumar earned his PhD from Tokyo Institute of Technology and collaborated with several eminent international researchers and academicians, such as Professor Boulanger from USC Davis, Professor Gabriele Chiaro from University of Canterbury, Professor Oishi from Kobe, and Professor Bayat from ETU Turkey. He's a recipient of prestigious fellowships, and for the past couple of years, Dr. Kumar is actively working in the field of SPH-based numerical modeling of large deformations geohazard, which is, I guess, the main topic of his talk. So, Dr. Kumar, please go ahead. The floor is yours.
Thank you, Professor Samuel, for a kind introduction. Let me just share my screen.
Yeah, sure.
I hope you can see my screen now.
Yes, there is not a presentation. Okay. Now we see the presentation. Okay, here we go.
Okay, so thank you again. Let me first thank Professor Satyam for having me on board on this 2 days workshop. Yesterday, all the sessions were really good, very informative, and we had good time attending all the sessions. And I hope the same for today's lectures as well. The topic of my talk today is SPH-based numerical investigation to evaluate the effects of debris flow or large deformation, I would say, on associated built environment. So we're targeting a physics-based framework to model the large deformation problems. And let me notice the contributors. My first PhD student, Nadia Mubarak, and passed out master student, Pranay Kumar, who have contributed in the subject matter, which is going to be presented in today's presentation. So in the last yesterday's sessions, a lot of comprehensive background has been set regarding the worldwide landslide hazard scenarios. How do we deal with it? What are the complications? How do we do, what are the current practices, and what are the current improvement which is going on in terms of early warning of the landslides? But again, just to set up very briefly the background regarding my talk. So this is the scenario of worldwide hazard landslide hazard. And as of now, there is a lack of, comprehensive and, unified catalog for the landslide hazard. So the report published by GLC Global Landslide Catalog, NASA and USGS in collaboration, they have estimated the fatalities for, almost in all the continents of this world. As you can see the scenario within, Himalayan region, Meghalaya Plateau, and also the Western Ghats of India, we can see the Indian subcontinents are highly susceptible to landslide and induced hazards. Not exactly the same way, but European regions and major economies like Italy, France, and Germany, they are also dealing with the large deformation problems like landslides, debris, and snow avalanches. So this is not a country-specific problem. This is a worldwide issue, and it's a good news that a lot of researchers are coming together, to tackle the different aspects associated with landslides and induced impacts on the built environment. Just to have closer look, this slide shows the number of fatalities, including landslides, excluding the co-seismic events, and the deaths which are recorded. Of course, there are so many instances where the events are not recorded. So this statistics is just to give an idea to understand the gravity of landslide hazard induced fatalities across the world. So the deaths are nearly 20,000, economic losses more than $1 billion US dollars for one country, and the population affected as of now is nearly 5 million. So that's a huge number. And the land area which is being affected by the landslides is around 4.2 million square kilometer, which is like 90% of total area of India. So design a framework which can tackle several issues associated with the landslides. Okay, so let's talk about the challenges. What are the biggest challenge associated with the landslide is when it is going to occur, how big is going to be the event, and what is the impact, the socio-economic impact on the associated built environment. So when I say when, this comes under early warning systems, there are a lot of recent pretty good advancement in terms of research to better understand the early warnings. How big, we need to understand what is the influence distance, what is the runout distance. This is actually a major concern when we talk about the landslides. The runout distance, because we have large velocity, huge depth, and sometimes this runout distance is tens of meters, which affect the surrounded area. So this is a major concern, and poor predictability even make this problem more challenging. So if we can better understand how big is going to be landslide, so we can better understand the impact of the landslide. So these three are the major challenges. Let me talk about the phenomena. So the landslides, the technical definition as we take it for the large deformation problem, can be regarded as coupled geo-hydromechanical phenomena. So there is a coupling behavior of geology, hydrology, and the mechanical characteristics between physical properties of the landslide material that usually initiate on steep slopes. It can of course happen on gentle slopes, but on steep slopes usually involves fast flow along the confined channel, which is specifically case for the debris flow, and then it deposit in the flat areas. Now, to better understand the characteristics, engineering characteristics, so this landslide or debris flow are multi-phase transition and interaction problems. So we don't only have solids, there are solids, there are fluid, there are air interruption. So it's a multi-phase transition and interaction problem. So numerically modeling this kind of problem is very, very challenging. There is complicated mathematics formulation behind it. There is a wide range of geological characteristics. We do have, driftwoods, we do have boulders, we do have gravels, different mixture of soils interact with the air and the water. So there is a wide range of geological characteristics. So we don't have a uniform material across the landslide or debris. there is a collision and coexistence between solid and fluid behavior. So this is even more challenging to address numerically. So let's say we do have two phases separately. We have mathematical formulations to add that kind of characteristics. But when the sliding is going downwards, there will be collisions between two phases and also coexistence. They can exist simultaneously. So to formulate the constitutive formulation for such kind of complex mechanism actually is very, very challenging. So this is one of the biggest challenge. There are fast flow velocities, large impact forces, and long run out, like I mentioned before. In addition to poor predictability make this problem even more challenging. So how do we do that? How do we go ahead while addressing these challenges, which I discussed in the last and this current slide? So our research is based on SPH modeling, where we model the domain, the soil domain, with the help of smooth particles. SPH is a smooth particle hydrodynamics, which used to be used widely in astrophysics. But for the past 5 years, 10 years, this has been extensively used for mechanics, solid mechanics, hydrodynamics, and also geomechanics. So we'll see in brief how do we use SPH to better numerically simulate the landslides or large deformation problems per se. The next concept which we are clubbing is data simulation. This is a quite novel technique which we are implementing, and you will see how data simulation is helping us to better simulate large deformation problems. So data simulation is a technique where we club the physics with the observed data. So we do, of course, the physics will never be exactly 100% accurate because these complications which I have just mentioned. But with the help of observed data, because we are also monitoring the site-specific, ground deformations. So if we club these two together, we do have, remarkable accuracy in terms of prediction of landslides. These are highly computationally challenging, so we have to use high-performance computing facilities. And clubbing all these three, we are developing a risk and reliability framework. Okay, so let's take one by one. So what is SPH? So smooth particle hydrodynamics, in short SPH, is a computational method used for simulating the mechanics of container media, such as solid mechanics and fluid flow. So what do we do? This SPH is a mesh-free Lagrangian method, unlike FEM, the finite element method, where it's okay to use for the solid mechanics problem, the FEM, or conventional numerical simulation, but landslides and debris are large deformation problems, so there are issues of mesh distortion. So conventional FEM method won't work to predict long run out distances, but because SPH is a mesh-free Lagrangian method, so that's one of the optimal choice for us. This is suitable for modeling of large deformation problem, like I mentioned, and the domain is discretized with appropriate number of particles. So let me just first take the fundamental theory about SPH. So this is the support domain depending on the smoothing length, and we do have kernel function which is used to interpolate the properties. Let's say we define this is a slope, and we do have two different triggering factors, rainfall and seismic action. And the whole domain is discretized with the appropriate number of particles. So now the question is how these particles are interacting with each other. And this definition of interaction is based on this kernel function and the weightage of particular point, which depends how far it is from the supporting domain or how close it is with the the median of the kernel functions. So the particles within this domain will be interacting with each other based on their individual physical properties. And using this concept of SPH, we can see here we will be able to model the large deformation, and also will be able to assess the impact on the build structures. The next one is data simulation. How do we club data simulation with SPH? Just imagine, let's say this is the initial phase of the landslide and start taking place. When we do numerical simulation, the typical numerical simulation, we assume constant properties, let's say the density, the viscosity. But just imagine if you try to visualize, the scenario is going to be changed along the run out distance, right? These properties are not the constant. So to better capture the mechanics of the debris or landslide, what we're trying to do is we are taking as the input parameters, let's say the density or viscosity or the void distribution, and we club it with the observed information and try to forecast one ensemble. And this ensemble is treated in the analysis window with respect to the observations. And we predict the forecast for these, our point of interest, like density and the viscosity. And we trying to change it a spatial temporally, a spatial variation, and also temporal variation we are able to capture. And we club this dynamic behavior with the SPH formulation so that we don't lose out the important information on properties associated which are affecting the landslides in general. So the principle of data assimilation is to combine different sources of information and to obtain a more reliable approximation of the state variables. So in our case, state variables for the landslides are, let's say, viscosity and density, and also water content. And this can be defined as a physical field for a sequence of parameters. So our investigation schemes involve these flow charts. So we do have material properties, interparticle distances, and the initial geometry, which we give as an input. And then we define the execution parameters. There is a long list of execution parameters. We do have different types of kernel functions. We have used cubic spline, but there are a couple of more available. What is the integration scheme? We need to specify the artificial viscosity for the numerical stability. The boundary condition is one of the biggest challenge in SPH, but we do have a couple of ways to tackle this problem. And we need to define the tensile stability constitutive models to capture the physics, and then we perform the analysis. In the post-processing phase, we usually try to get what is the velocity gradient, what is the strain distribution, stress distribution, and runout distances. I won't be going into mathematical details. If someone is interested how to model the kernel integration scheme and all, please feel free to contact me. Okay, so now the question is, we need to first validate our the algorithm which we have developed. Me and Nadia, actually Nadia Mubarak is working on this problem for last 2 years. She's doing actually pretty good job. So she must be in the audience, I assume. So we first need to validate this problem. And one of the, the fundamental validation is if we can simulate the internal properties, the angle of internal friction. So imagine there is a standing column of granular soil, sand soil, and definitely it is not stable because there is no cohesion. So if we just remove this plate, so this will retain, the angle which is equal to angle of internal friction. So let's see if we are able to, okay, this is strange. We were supposed to see one animation here. Just give me 1 sec, please. Oh, so it seems animations are not working. I think now it's working. Okay, so this is the animation. So you can see here when we remove the side plates. So this is, going to take the slope which is equal to internal angle of friction. So this is one of the, most fundamental simulation which we have to carry out to justify whether our algorithms which we have developed is able to capture the, the fundamental physics of the soil properties. Okay, so the next, so these are the instances at different time steps. At t is equal to 0, and the slope is going to take place, the final shape at t is equal to almost 1 minute. Oh, okay, so I forgot to mention this was the physical testing done by Professor Bui et al. And his team, one of the pioneer guy who is doing pretty good job implementing SPH for large deformation problems. And this is our, simulation. So I think our simulation is doing pretty good job in terms of capturing the, testing results, the failure surface, and also as well as the final, the deformation phase. Okay, so someone might ask this question because in my last 2-3 slides, I mentioned, okay, this debris flow and large deformation problems, landslides are, very complex. There is multi phases. We have coexistence and collision between different phases. and how can we validate our algorithm using the, this very simple version of test case. So in that case, because we have to ensure that our model is able to capture the fundamental physics. So now we have simulated one real landslides which took place in Dangguo, China, triggered due to Wenchuan earthquake in 2008. So this is the topography where based on Huang et al. Published in 2012, and we took the same scenario and tried to simulate whether our model is able to capture the landslide or not. So this is where our model is able to, see, you can see this is the failure surface where along with the landslide occurred. And if you have a look, our algorithm is able to capture the this landslides with remarkable accuracy. So before I start telling good things about our algorithms, let me say the limitations of our algorithms. So you can see here a couple of particles are still there, which is actually not the real case. So because this work is in still work in progress, we are developing our algorithms. We have started from the very scratch. So we still have a long way to go, but as you can see, this particle actually is traveling without any ticket. So if you have a look here, just try to see this particle is flowing really far. So this kind of numerical stability we are still fixing. But overall, our developed model is able to capture, the essence of these landslides. We'll see, we'll compare it in our next slides. We also did a couple of analyses based on changing the smoothing length, interparticle distances to see in which case, because we have to do trial and error method, how many number of particles are sent, what should be the supporting domain. So based on these different numbers, we were able to capture even the closer view of this Wenchuan, this landslide which occurred in China. So this is the summary of post-failure topography, simulated and actual with respect to the pre-failure topography. So this red dotted line shows the pre-failure topography. The black one is the failure, which was the actual. As you can see in the beginning phase, our model able to capture the failure surface with remarkable accuracy. Actually, this is really, really good in terms of accuracy. The problem which we are having here in this zone, if we have an overall view, this is not significant, but because we are researchers, so we are trying to identify what might be the reason why we are, even the volume is same, but why our line is a little bit above the black line. So there are a couple of issues. Those issues are, some of those issues are, we still fixing, try to the void redistribution between different particles. There are some particles which are not stable. And also the phases, because the landslides again is complex, but we have considered only the solid and the fluid phases in this. So that might be one of the limitations. So we are trying to incorporate all those limitations, and I think very soon we'll have even better approximation of the landslides. So after validating these two cases, one is for the standing column, one is for the existing landslides, I think we have this confidence that we can, if we are simulating something, we can make some sense out of our numerical simulation, because this is very, very important. If we do numerical simulation, this is always very important that we justify our algorithms, our numerical codes, and then only we can say, okay, the kind of results which we are producing make some sense. So we simulated Rishiganga tragedy, which I think occurred in 2021, February or March, I forgot the month, where there was a huge debris flow, and that impacted this, power plant. There was huge damage to one of the power plants. So this was the initiation point where debris started, and this was the main structure which suffered major loss. So with the help of our numerical code, we are trying to assess what is the impact and how to reduce this impact on this, main structure. So to understand the behavior, what is the flow velocity, how much is the long run now distances, what is the flow depth, we have selected 2 points, location 1, which is very close to the initiation of debris, and also location 2, which is close to the main structures. We have provided one solution in terms of barrier. One professor from Hong Kong, HK University, is doing, very cutting frontiers research, trying to modify these barriers and trying to simulate actual scenario. But because we are in the early phase of our our research in this area. So we have considered it as a concrete block. We haven't considered the meshing of the wire. How do we model the geometry? So first we extracted the 3D domain of reaching a region using Blender software, which is openly available, open source software. And we clubbed this 2D with the DEM model and tried to find out the STL file for the 3D domain. It's not that complicated. It may sound complicated, but it's easy. And this is the location where the debris, started. The debris are initiated. So the volume of this debris, I think, was around 73,000 cubic meter, which is actually huge. And this is the place where the structure, got damaged during when the debris impacted on this structure. So we do have 3 different scenarios. In one case, we simulated the actual scenario. In one case, we have provided the barrier structure, but we given only one barrier just to restrict the flow and the depth of the debris which is coming for this main structure. And in third case, we provided the same barrier structures, but we refined the openings. The area is same to see in which case the performance is better to reduce the impact on the built environment. Okay, so let's say for the first case when there is no structure on upstream. So let's first see the animation. So when there is no structure on the upstream, the debris is coming down and impacting this structure. And you can see the velocities at different time steps. In the beginning, at the location 1, which is somewhere here, all the particles mean the whole debris is having around 16 meters per second velocity, which is quite huge. And you can see the closer view the moment it is impacting the main structure. So the moment it is reaching here, you can see all the particles are having the maximum velocity somewhere here. And then you can see here the moment it impacts the structures, there is a significant amount of velocity, and slowly there is a reduction in the velocity. But this impact, how much is the impact, we'll see in the coming slides. But if there is no barrier structures, the whole debris is going to impact with full capacity to this main structure. Let's see if we have one passage, there is a barrier structure and there is one passage, to see if we are able to reduce the magnitude of the velocity, of this debris. So you can see here the first scenario is almost the same, but after passing through these barrier structures, the scenario has been changed. We'll see whether this is significant or not in our next slides. But as you can recall the previous slide, here there is no change because the debris is going to first impact this barrier structure, and then it passes through this opening and then impact the main structures. So in the beginning, more or less the same, but the scenario here has been changed significantly. In our third case, we have provided 2 passages upstream, and you can see even a better performance. Even though the total area of the opening is same, but we, instead of giving 1 passage, we gave 2 passages. And we'll explain why this is performing even better when we discuss the impact forces. Okay, so now let's see, this was the behavior in terms of the velocity, the flow velocity of debris. Now let's see what is the force on the barrier structure and force on the main structure. So let me first talk about the main structure. The first one, no barrier on upstream, the true reality where we don't have any mitigation measure. So you can see the moment it strike the main structure is around 5 seconds, and there is a huge force on the main structure, which is around 300 meganewton, not less. Actually, it's quite big number. But if we have barrier with 1 passage, the blue line and the red line, so we can see there is a significant reduction in terms of the force which is going to impact. But after around 20 seconds or 16 seconds, the behavior is more or less the same. The reason for this is, for all the cases, even if we have the barrier structure on upstream side with 1 opening or 2 opening, doesn't matter. After 15 or 20 seconds, the water is almost reaching towards the main structures, because we are restricting the flow to some extent, but the water still, or the debris is still approaching to the main structures. So our concern is within this range, whether we are able to reduce the impact force or not, and providing barrier with 1 passage, 2 passages, I think our mitigation measure is doing pretty good job. That's just the simulations, because we haven't simulated the actual barrier, because where we have the wire missing. That is our current ongoing process. But just to see whether the opening makes sense or not, we took the same concrete structures. This is the force on the barrier, because this is the beginning. The debris is directly striking the barrier structures. Definitely, we are not going to see any difference. There is a couple of difference. There is a minimal difference in the later phase, because if we have one passage, which is the red line, it is going, faster. If we have two passages, because of the boundary between two passages, going a little bit restrictions. In terms of flow depth, if we have at the location 1, because this is going to be the same for all the cases, so let's have a little bit more focus on the location 2, because the debris is coming out from the barrier structures. The green line, the no barrier on upstream, there is a huge difference in flow depth. The flow depth here is significantly higher in case we don't have any barrier. But by providing the mitigation in terms of barrier with one opening or two opening, we are able to reduce the velocity, and we are also able to reduce the flow depth. And this is the scenario for the velocity, like I mentioned, for the location 2, because location 1, we directly the debris is coming towards his, so we can see a lot of similarity. You can see a little bit jump here and there, because once the debris is approaching barrier structure, they will be bounced back of some of the debris. So you can see a little bit jump here and there. But for the location 2, there is significant decrease in terms of velocity if we compare with the green signals towards black and red signals. So with this, we were able to estimate the impact which is coming on the main structure due to this debris flow. And also what can we do to avoid huge damages. So the provision of barrier structures for such important structure, I think, makes sense. And we are also able to evaluate quantitatively. Perhaps there are some limitations, because we are making certain approximations, but qualitatively these results make more sense. So just to take away from this presentation, the large deformation problems, geohazards like landslides, debris, avalanche, are common disaster in hilly areas, and it's responsible for large economic and social loss worldwide, which we all know, which we will agree. Actually, everyone of us will agree with that. Now, these geohazards can be regarded as coupled geo-hydromechanical phenomena that initiate, generally on steep slopes, involve fast flow along the confined channel, and then deposit in the flat areas. Based on our understanding, again, this work is in still progress, but we're doing a lot of improvement from time to time. And our, contribution from this work is already in review phase. We have received pretty good comments on our publication. Soon, I think it will be online. And the SPH-based numerical modeling can capture the physics of large deformation problem. And I think it's highly effective. A lot of research has to be done just to capture, the different phases of the problem. But based on our experience, we can say this will be a remarkable accuracy if we can implement SPH to capture the large deformation problem. And if we can club it with the data assimilation algorithm, so we can also capture the temporal and spatial variation in different physical properties, which will even enhance the capacity of our algorithms. So yeah, thank you so much for your kind attention.
Thank you so much, Dr. Kumar, for your nice presentation, your nice talk. I ask if we have questions from the public.
Thank you, Professor.
Good afternoon, sir.
Hello, good afternoon.
Sir, can you a little bit give more specifically on the boundary condition you have used on the bed, sir?
Sorry, say again.
So what kind of boundary condition you have assumed in the bed slope, sir?
Boundary condition for the landslide problem, right?
Yes, sir. In the bed, sir.
In the
Bed. Bed.
Okay. So we do have 3D domain, right, which we extracted using STL files, and what we did is we estimated the amount of debris flow which occurred in receiving regions, and we imposed that debris flow on that surface. So there is some amount of based on the viscosity, there's some amount of friction between the surface, but the surface or the terrain is giving the flow in which direction the debris is going to flow. So there is no specific boundary condition in that, but the kind of simulation which we did, the validation purpose, we do have boundary conditions so that the particles should not detach from the boundary, which is actually the major concern if we use SPS formulations.
Yes, sir. Thank you.
Okay.
Any other questions?
So one more question, sir.
Yes.
So because of this irregularity in the terrain, so there will be the volume entrainment also, sir. Your model does allow some kind of entrainment as well?
Yes, so our model can deal with the hydro, means the water, the geo and mechanical characteristics. But again, still we are not able, we are, working to capture the coexistence between these different phases. So at this moment, we are not taking into account the collision between 3 different phases, but yes, we are taking into account all 3 different phases.
In your debris flow study, you have used the same debris sizes are uniform, or it was varying sizes?
Yes, that's a good question. So again, at this time, the particle size is same, but we have changed the physical properties based on the site reports. So the properties varying with respect to data simulations we have clubbed, but the particle size is same.
Okay, but then velocity will change, when the particle size changes, velocity also will change,
Yes, so at this moment we are considering coherent material. So like, of course, we will have the driftwoods, we'll have different boulder size and gravel size. So we are taking the properties which justify the average of debris flow. But yes, of course, we need to model the driftwoods, the different shape of the boulders. Sometimes even we have big rock. Yeah, so that is work in progress. Yes, this is again still in the beginning phase.
Yeah, but I have heard when I attended a conference in Taipei that they have got a separate flume-like arrangement for the debris flow, monitor or simulate the debris flow and then try taking the measurements. Is there
Yes. Some people are able to do it, but like we have started on 1.5 years ago only in this field, because either we need to buy or we need to write everything from the scratch. So for us, it will take some time, but we are going ahead on the same path.
Yeah, but do you think that in our some of the landslides that have taken place in our country, debris flow was dominant?
Sorry, say again.
No, some of the landslides which have taken place in the recent times, say like for example in Kerala and other places,
yes,
flow was really so dominant.
I think yes. Actually, I didn't get your question. So can you please repeat again?
I'll just, Dr. Ritesh, the question is like Balakumar sir is asking, in the recent past, in the last 3-4 years, the predominantly debris slides are more in the country, either in the Western Ghats or in the Himalayan region. So yes, sir, it is very predominant.
Yes.
Okay, fine. Thank you.
Thank you so much.
So thank you so much, Dr. Ritesh. It was such a nice presentation.
Thank you so much for having me on board. I really appreciate that. Thank you.
Can I have a very quick question? More than
Yes,
a
please.
question, is just a curiosity. How much time does it take to have a simulation with your SPH? Is that fast, or do you need a lot of time?
No, this is computationally very challenging actually. So it takes time. So that's why we have to use SPC computers. We do have a mini supercomputer access to our department. So we are using that. So I think 2-3 days that took to simulate this debris, the landslide which we saw now on validation, 2-3 days.
Okay, so I guess it depends also on the size of the
yes,
site.
exactly. If we try to improve the accuracy, we have to model the minute details, the number of particles, the smoothing length.
Yeah.
And
Yeah, so
that is
also
going to be
the model complexity, I think.
exactly.
Yeah.
So the number of phases we include, the number of interactions we are going to include if we club it with data simulations. Definitely computationally challenging, but there are some ways to, let's say we want to understand the dynamics during an earthquake. So we can see what are the peaks which can cause, which can trigger the landslides. And instead of taking the whole earthquake, we can just take those couple of peaks. So there are some ways to, minimize the computational effort.
Yeah. And so
Yeah.
I think in this phase of the research, you are mainly doing back analysis, I think. So I think you can pay a lot of attention of details. Is that right?
Yes.
Yeah. Why maybe for, I don't know, maybe it's too premature to think about real-time application or
True. So for the real-time application, so what we are trying to do is we don't want to miss the physics, the initiation at what time and which location of the slip surface, and then we'll club it with the data simulation algorithms, because we do have some empirical models, right? Let's say I think sigma model also one of the empirical formulation. If we club it with the physics, definitely it's going to improve the efficiency. So there are some empirical formulations which we are going to club, but first our main focus is to capture the physics, because for us, I think that is one of the fundamental requirement.
Yeah, it's a very interesting point, because this is a field of applications where the physics meets also the technical constraints. So you have to balance both of them. Thank you. Very interesting. Thank you very much.
Thank you so much. Thank you.
Hello, Professor. Good afternoon. Hello. Yes. Dr. Ritesh Kumar. Hello.
Yes.
Yes, sir. Sir, I am a practicing engineer. Just for my curiosity, as you have told in the very introduction, that since it is a debris flow, that's why the mass is discontinuum. That's why discrete element modeling means DEM is to be made best, as you have done some rigorous research. But as far as other modes of landslide failure is concerned, like rotational failure or transitional mode of failure, where continuity of mass can be considered, in that case, FEM modeling can be valid, huh?
Yes, definitely. And also these days, because it's a very heterogeneous material, right? So people are also using clubbing it with MPM, the material point method, and also DEM. So the hybridization of these techniques actually is more effective to tackle generalized landslides.
Okay. Sir, is there any commercial software available for doing such type of modeling, numerical modeling in practice?
As of now, no. So there are some open source software, but like I mentioned, in astrophysics, they are tackling some problems, hydrodynamics, but for the landslides, we don't have. There are a couple of open source, but they are very specific. So you need to use that and you need to do the coding by yourselves. But I think in future, very soon, we're going to have some open source softwares dedicated to landslides.
Great. And the last, just for my curiosity, sir, do you propose any kind of analytical method of analysis in addition to numerical method? Because numerical gives the more strain deformation related issues.
Yes. So what we're trying to do is, based on these, sophisticated 3D, 2D simulations, we will capture the features which affects those particular landslides. And we'll do that, the empirical formulation based on that. It's like based on 3D models, we will club. But again, those empirical formulation will have certain limitations. But make some estimations, we can use those. Yes.
Yeah. As you told that for doing numerical simulations, it needs a special coding as well as time. So as far as for rough approximate analysis to get an impact of the effect, if we can such kind of analytical method is also available. Okay, sir.
Ultimate goal is to come up with the empirical formulations. Like we have Newmark method. No, there is a formulation based on how to take into account the seismic coefficients. But only PGA is not the causing factor. There are several other factors. So we will improve those equations. But first, we want to capture the physics. That's our main focus at this.
Okay, sir. So, very interesting and comprehensive. Thank you so much, my regards.
Thank you so much. Thank you. Appreciate that.
Any other questions from the public? If not, I thank again Dr. Ritesh Kumar for his nice presentation. I appreciate your effort to stick to the physics of the modeling without compromises to technical constraints. Very nice presentation. My compliments.
Thank you so much.
I think we can move forward. We are a little bit ahead of the schedule. So the next speaker will be Tommaso Carlà from the University of Florence. He's a researcher of the Earth Science Department and is also a member of the Civil Protection Center of the university. He is a geologist. He has a PhD in Earth Sciences, and he also was a visiting researcher at the University of Alberta. In his PhD, he specialized in rock mechanics and remote sensing. At present, his main expertise is ground-based remote sensing, including but not limited to laser scanners, ground-based interferometric radar, and Doppler radar. I'm not an expert on that, but as far as I know, is a rather innovative technique, and Tommaso will explain better this new technique. I would like to stress that Tommaso, in his researches, is specialized in linking monitoring duties with early warning and risk management in emergency scenarios, working in close collaboration with civil protection, also at the national level, and also with local authorities. So Tommaso will give his talk with the title Interferometric and Doppler-based monitoring and management of slope hazards. So Tommaso, please go ahead. We are ahead of the schedule, so take your time, and the floor is yours.
Thank you. Can you hear me well?
Yeah, we can hear you very well.
And you can see the presentation.
We can see the screen, but it is not in presentation mode.
Okay, let me try again. Can you see it now?
We see the screen, but still not in presentation mode. We see the small icons on the left. Here we go.
Okay, you can see. Perfect. So thank you very much. As Dr. Segoni said, I'm mostly interested in rock slope stability and management of related slope hazards. But so this presentation will be, has been prepared with the rock slope stability problems in mind, but that doesn't mean that the techniques that I am about to talk about are restricted to those kind of problems. They also can be employed in certain types, at least, of soil slides. I have chosen to talk about these two techniques, interferometric radar and Doppler radar, because they can be classified as two separate types of techniques. One that works in the early warning phase of landslide monitoring or rock slope monitoring, and that we can say it can be employed as a proper alarm system. What do I mean with those two terms? For early warning, let me just activate the laser pointer. Early warning, what do I mean with early warning? These are phenomena that undergo what some researchers say is a slow to fast transition. That meaning that, for example, large rock slopes, they may creep slowly at rates of millimeters to centimeters per day or per month or even per year for a very, very long time, and for tens to hundreds to thousands of years, and then may undergo a rapid transition to, they may undergo failure, meaning that they may suddenly attain very rapid velocity, extremely rapid velocities in the order of meters per second. So having a sudden drop of cohesion within the slope and then rapid propagation of the failed material. The thing is that these failures are usually anticipated by a more or less long period of accelerated slow displacements, and measure these slow displacements and analyze them in order to try to predict whether a failure is about to occur. And that's why we call early warning system. We talk about ground-based radar interferometry as an early warning system. On the other hand, there are other types of phenomena, namely, above all, rockfall, that are, we can say, that are basically unpredictable, because precursory displacements are, if they exist, are very, very little, so they are very hard to detect. They are also very spatially predictable phenomena. So if you have a large rock slope, rockfalls may occur from many potential source areas. And therefore, for this reason, we cannot perform early warning for this type of phenomena. And therefore, we need something, if we want to employ monitoring, we need something that can tell us in real time, in proper real time, whether rockfall is occurring or not, and therefore take action to limit the accessibility of people to the area of risk. And we call these Doppler radar alarm systems. We will, this is going to be in the second part of the presentation. Of course, it's going to be focused on rockfalls, but it may also be applied on other types of unpredictable, extremely rapid phenomena, such as rainfall, debris avalanches. So phenomena that are not preceded by precursory displacements. So we'll immediately get into the specific, not so much into the specifics, but into the general principles of ground-based radar interferometry. I think many of you, or at least several of you, has already a good understanding of the technique, because it's not, we can say that it's no longer a groundbreaking technique, but it's becoming more conventional now. In around for a good decade or even more than a decade. And we can now probably say that it's the more advanced tool for measuring slope to moderate slope displacements, because it is able, as you can see on the right, to create spatially continuous and temporally continuous maps of slope displacement. And of course, we can have multiple purposes. This technique serves multiple purposes for landslide characterization and the kinematic characterization, but are strictly talking about hazard management and safety of people. The most important aspect is that this instrument is able to, as I said, measure displacements both in space and time at high resolution, and therefore it's the best tool we have to measure those kind of accelerating displacements that you see in the plot to the left, that usually precede the larger rock slope failures. There are two main types of ground-based interferometric radar. One is called real aperture radar, and the other are called synthetic aperture radar. What's the difference between them? Real aperture radar, I like to refer to them like they more or less work like total stations. So you have a single antenna, which has the shape of usually of a parabola, that works like basically like a total station. What that does mean? That the antenna rotates on a fixed pole and illuminates the rock slope one pixel after the other, okay? Like you see in the animation here. there's not a lot of difference in the final measurement accuracy and resolution of the and spatial resolution of between real aperture radar and synthetic aperture radar. The main difference is that real aperture radar typically takes a little bit more time to perform a single acquisition because, as you can see in the animation, the slope is illuminated one pixel after the other. And the other important thing is that to attain a very good resolution, high resolution of the slope, you need a very big antenna, meaning that pixel size, as you can see here, is inversely proportional to the size of the antenna. Therefore, if you want to have a good resolution, you have to have a very big antenna, which is in many situations not practical. And also very large antennas are, of course, more sensitive to ground vibrations or other kinds of disturbances. So, for example, in open pit mines, that can be a problem where vibrations are frequent. Synthetic aperture radar is the most common, has become the most common solution, and that's because the instrument itself is much more compact. You see it here, it's this little yellow box represented by this little yellow box. Is equipped with a very little transmitting antenna and a very little receiving antenna. And instead of these are small, and the extent of the field of view is obtained by the instrument move in steps along a predefined path, usually a mechanical linear rail. And at each step during the travel from one end of the rail to the other, the instrument acquires a single radar image. And then when it arrives at the end of the rail, all the images that were acquired during the path are coherently summed up together. And that creates, as the name suggests, a synthetic radar image that that covers a very large field of view, but that is composed of many, of several more little radar images. And in this case, so attaining a higher resolution is easier, and specifically the range resolution is constant that depends on the speed of light and the B, that is the bandwidth employed by the transmitting in the transmitting microwave. And the cross range resolution, or also called the azimuth resolution, is dependent upon the wavelength, employed wavelength. Usually nowadays instruments use the KU band, and depends upon the length of the rail. Okay, so this solution is more often employed today because, of course, it's still kind of a large equipment, but more compact and can be separated into single smaller components. Whereas in the case of real aperture radar, you have just one big, very big single component. Regardless of real aperture or synthetic aperture, the final goal is to perform the so-called interferometric analysis, which is here schematized, and is basically performed by comparing two radar images acquired at different times. And specifically, what goal is to compare the phase information between the receiving microwave in the first acquisition and the received microwave in the second acquisition. I didn't say this before. Maybe I should mention it, even if it's quite understandable. The goal is to transmit the microwave towards the slope, and then, of course, the slope reflects back that information, that wave towards the instrument, and so the instrument is able both to transmit and to receive the backscattered signal. And so the goal of the interferometric analysis is to compare the phase information between the measured between the first acquisition at time t1 and the second acquisition at time t2. These so-called phase shift can be in ground-based applications, can be substantially reduced to two components. One is the true displacement of the slope between the two acquisitions, and the other is due to atmospheric effect, or also the so-called atmospheric phase screen. This is easily dealt with by knowing a certain part of the monitor of the illuminated scenario that we are sure is stable. So by comparing the phase shift that is in the what is presumed to be the stable area of the slope, we can filter that out in other areas that we are not sure are stable. And so we finally have just the phase shift that is due to displacement. This process is theoretical, but we will see later that is not always that easy. Here is just some examples of various models of what is also called the generally slope stability radar, regardless of whether it's real aperture or synthetic aperture. As you can see, here you have the common configuration along the mechanical linear rail, but and here you have an example of real aperture radar with a very big antenna mounted on a trailer. There are some more streamlined solutions where you have a synthetic radar that is also mounted on a trailer that you can just transport from one place to the other very easily. This is often done in mining operations. You also have synthetic aperture radar that work on a mechanical arm like this one, that also actually doesn't form linear movement, but a rotational movement. So these kind of instruments, which are kind of new, the newest in the field, they also provide some sort of three-dimensional displacement information, and other just work on tripods, and some also usually require some kind of protection shed like this one. So these solutions are for more stable installations that are more common in natural slopes rather than artificially blasted slopes. So I would like now to, I thought it was now convenient to give a list of features or advantages of ground-based radar interferometry, and also a list of downsides of ground-based radar interferometry. The main probably advantage is that the instrument can, at least in principle, operate regardless of lighting, that is both day and night, and the atmospheric conditions. So both in sunny, with sunny and fine weather, but also foggy or cloudy weather, as you can see on the right. It has, of course, a remote monitoring capability, but this remote monitoring capability is quite significant because the instrument works up to distances of a few kilometers. That means that the instrumentation itself has basically no chances of being damaged by the slide movement itself. Like this can often happen, for example, for in situ instrumentation, like I don't know, inclinometers, extensometers, prisms, etc., which of course can be damaged by they are installed on the actually unstable slope. So if the slope moves too much, they may be damaged. The radar, on the other hand, can be installed at several kilometers of up to a few kilometers of distance to the slope of crest. And that means, for example, in a valley, you can have the slope instability on one side of the valley and the radar on the other side of the valley. So perfectly at a perfectly safe location. The accuracy, or at least the theoretical accuracy of the displacements, is very high, up to sub-millimetric accuracy. And also the spatial resolution is very high. It can vary, typically varies from metric spatial resolution up to down to decimetric spatial resolution. Here you have an example of a real case study. This actually wasn't a landslide, it was an unstable section of a medieval city wall in a town, in a medieval town near Florence, here near Florence. So you can see that the part of wall that was actually unstable was very accurate, could be very accurately delimited based on just 4 days of displacement measurements. And you can see these displacements refer to the period between 19 and 22 February of 2014. And this is the outcome about 10 weeks later. So the section of unstable was very precisely delimited based on the radar data. As I mentioned before, measurements are also not only at a very high spatial resolution, but also spatially continuous. That means for very large phenomena, like you can see these very large earth flow on in the time-lapse image, you can distinguish different kinematically distinct areas of the landslide. You can see on the displacement underneath. And so, of course, you can distinguish different parts of the landslide based on characteristic velocity and also sensitivity to triggers. And of course, this is there is no need to say why this is very useful for hazard management. For each pixel within the radar image, a pixel is a sufficiently coherent target, meaning that a target that is capable of reflecting the transmitted microwave with sufficient coherence and at sufficient intensity. For each pixel of the radar map, we can extract the displacement time series from any radar pixel, manually selected radar pixel, and of course displacement and also velocity. The acquisition times of the instrumentation is also very high. It depends on the system configuration, meaning, for example, in the case of synthetic aperture radar, the length of the mechanical linear rail, and also on how fast or on the number of steps that I want to perform along the rail. So these can vary between usually some minutes down to 1 minute, roughly 20 or 30 seconds. So that's very competitive with respect, for example, to an instrument like robotic total stations or terrestrial laser scanner that at best in the most favorable configuration can perform an acquisition in just under 10 minutes. And of course, much better than interferometry performed from satellite platforms, which takes several days. Nowadays, all these instrumentation can also be managed from remote, both in terms of configuration and analysis of data. So again, this is, of course, no need to say why this is a big advantage. So these data can be, instruments are now commercially available with also with software packages that can be used to create alarm maps, and also that can be used to communicate with alarm devices, like, for example, traffic lights or other kind of alarm devices, and also to send alarm messages via SMS or email. And lastly, the ground-based instrumentation has been, the ground-based radar, interferometric radar, has been proven to be to have an excellent integration with the satellite counterpart. So, for example, you have an example of a large and stable rock slope in the northwestern Alps, and you can see in the upper figure the colored dots represent satellite interferometric measurements from PS insert techniques, and you can see that the slide area is bounded by these orangish polygon, and you can see that the upper part of the slope is very well covered by satellite interferometric data. However, you have a little part here of the slide that is encircled by this white circle at the very toe of the slide that you have information here. And this is because the toe of the slide actually moves a lot faster than the rest of the slide, of this particular slide. And therefore, this is too quick for the sensitivity of the satellite techniques. On the other hand, we have a ground-based radar also installed right about here. And you can see in the lower picture that the toe of the slide is very well captured by the ground-based instrument. And you can see that indeed it does move a lot faster than the rest of the slide area upslope. But also on the other hand, you see that the upper part of the slide area, very little, there is very low number of pixels because of topographic, of the local morphology and shadowing effects. So the two techniques integrate with each other very well. Now, talking about disadvantages of the technique, regardless of this is of course more in the case of real aperture radar, but still also in the case of synthetic aperture radar, it's still large and heavy equipment. Not only that, but you need stable flat ground to install the equipment. So that's not always easily obtainable to find a suitable spot to install the instrumentation. And that's why sometimes there are operational limits that are imposed by the field of view and the distance that the instrument can work with. Like here, for example, you have to attain a very good point of view and favorable point of view. And in this regard, there's also another important downside, that is the displacement that is measured by the instrument is a one-dimensional displacement, 1D displacement. In particular, that represents the component of displacement, of a real displacement that is projected along the line of sight of the instrument, meaning the imaginary line that connects the instrument with the target. So for example, if you see here, you have the instrument here and let's hypothesize a radar pixel here. If the slope is unstable and moves in this direction, meaning roughly perpendicular to the line of sight of the instrument, then basically no displacement can be measured. Even if there is very large displacement, you cannot measure any of that. On the other hand, if the displacement were instead in this direction, represented by the blue line, so that is mostly roughly parallel to the instrument, then you can measure 100% of the true displacement. And you have to keep, of course, keeping that in mind when you decide where to install the instrument and what to monitor. Because most situations you will have an intermediate situation between the fully perpendicular and the fully parallel line of sight. And so you will measure a fraction of the total display, a more or less high fraction of the true displacement. And these, of course, also depends not only on the geometry of the slope, but also on the kind of failure mechanism. So this can change, for example, if the table is on slope because of flexural toppling or because of wedge failure or other kind of mechanism. So I've told you before that radar pixels can be identified only in sufficiently coherent over sufficiently coherent targets or parts of the slope. So that means that you have no data over areas covered by thick vegetation. So you may have slopes that are extensively covered with trees or other kind of vegetation. And so you have not so much spatially continuous information. You can see in this example where you have information, this is a very vegetated slope, and at the top of the slope you have a town, so you have information only basically coming from the buildings, but not in the lower part of the slope where there is vegetation. Another downside is that the measurement gaps in periodic campaigns may not be interpolated. That doesn't work like, for example, a robotic total station. So it's not convenient to do periodic measurement campaigns. If you decide to install the instrument, it's usually convenient to perform a full continuous monitoring campaign, because otherwise you will have gaps between the various campaigns that cannot be interpolated. As I said, the the line of sight of this instrument is very important. There are two kind of ambiguities that can be of information ambiguity that can arise. One is called rate ambiguity, but this is kind of not very frequent actually, because you want basically to install the instrument in a position so that the landslide travels toward the instrument. But however, in these, there are some rare occasions, this is mostly in rock slopes and basically specifically overhanging rock slopes, where the distance, where large strips or sections of the walls are found at the same line of sight distance from the instrument. And that means that the entire part of the slope that is seen at the same distance from the instrument will resolve it in a single pixel. And so that means you may have very high and very thin strips of pixels rather than rectangular or squared pixels. But so yeah, this is to be kept in mind, but it's very rare occurrence because of course overhanging rock slopes like these are not so much frequent. Then data, another downside that data may be affected by noise in case of rapid changes in weather. And as I mentioned before, this is especially a problem when you don't have what is called the correction area for the atmospheric phase screen. So for example, again, in the case of a very vegetated slope, it may be difficult to find a stable area that can be exploited for the correction of the atmospheric phase screen. And in these kind of situations, when you have rapid changes in weather, then you have these kind of artifacts that, of course, are not true displacement, but just due to noise. And then probably the most important thing to be kept in mind is the so-called phase ambiguity. This can make it difficult to monitor rapidly moving phenomena, meaning that there is a limit of characteristic velocity of the landslide this limit is imposed to ground-based radar interferometry monitoring, meaning that the displacement, specifically the displacement between two adjacent acquisitions, must be less than a quarter of the wavelength, of the employed wavelength. So usually we use wavelengths in the KU band that are roughly 17 millimeters long. So 1/4 of the wavelength of such a wavelength is about 4.5 millimeters. If in the time between two acquisitions, that can be, as I said before, from about 30 seconds to a few minutes, the displacement of the slope is bigger than 1/4 of the wavelength, that is 4.5 millimeters, where this negative sign means movement towards the center. Then you have the so-called duty issue. That is, you will actually measure like movement like on a clock, and you actually come here. That is actually apparently a positive displacement, which is not a positive displacement, but due to the fact that the phase information has done this path. Okay. And this can create these kind of artifacts that are called interferometric fringes, that are just a pattern of negative and positive displacements, apparently negative positive displacements. And the sum of these fringes will give you the true measured displacement. However, this cannot be done automatically, but you have to do that manually. And it's often can be done by an expert user that knows the technique. Here is an example of a paroxysmal inflation of this flank of the Stromboli volcano prior to a major explosion. And so this movement was very rapid, like it was about meters in a few minutes, less than a few minutes. And as you can see here, there is this very characteristic pattern of interferometric fringes. So to measure the actual displacement, you have to count the number of fringes and relate that to the number of phase cycles. So as you can see here, you count the first fringe, then the second one, and so on. Of course, a single cycle is half the wavelength. And so at the end of the count, you have, okay, 6 interferometric fringes. That means 6 times half the wavelength that is true displacement, 52 millimeters, so centimeters. But again, this cannot be done automatically. The instrument will give you, will give you a number that is not 52. It will give you just the number of the pixel. Okay, so between plus 4.4 and minus 4.4. If you want to get this number 52 millimeters, you have to do it manually, and this can be done only by interpretation of the user. So now that I finished with providing an overview of the technique, I want to very briefly give you an example, a practical example of a successfully monitored rock slope failure in the central Italian Alps. This was a recent failure that occurred in May of 2018, roughly 4 years ago, almost 5 years ago, actually. And, this particular failure occurred on a slope that was above a very important cultural heritage site that is called the Sanctuary of Gallivaggio, which is a cultural heritage site that was built in the 12th century, I think, so almost 800 years ago. And above this place, there was this very steep and roughly 500-meter high granitic rock slope. And at the very top of the rock slope, roughly here, it became apparent that there was this jutting and very fractured, almost disintegrated portion of rock mass that was about to fail. So a ground-based synthetic aperture radar was installed in valley flow, roughly here, to measure and monitor the displacements not only of this part of the slope, but of the entire slope. And it was instrumental in predicting down to the minute the exact time of this particular failure. As you can see here, this is the sequence of interferograms or interferogram maps in the minutes leading up to the failure. And you can see here the displacement is, of course, very well occurring. You just know that in this particular configuration, we were basically measuring position every minute. So roughly 3 millimeters of displacement in a single minute in this image. And then this subsequent image, you have increase of displacement. And then phase ambiguity, you see that it becomes yellow, meaning apparently movement away from the sensor. Then again, negative displacement, meaning movement towards the sensor, then you have failure. And this information was represented in a series of displacement time series of 10 radar pixels that very clearly showed an increase and accelerating displacement. And so we were able to predict the failure down to the minute. There will be another presentation later in the day that will more specifically talk about how to predict, to interpret these kind of data to predict the time of failure of rock slopes and landslides in general. So I'm done with the first part of interferometric radar, and now I would like to conclude in the second part of the presentation with alarm systems, more specifically Doppler radar. This is, as Dr. Segoni mentioned, actually we can say it's a groundbreaking innovative technique. It's been commercially available for just, I think. But its use is still not so common. So we can say that this is something new that has come into the market. And it applies to those kind of phenomena, as I said before, that cannot be predicted by means of precursory displacements. So landslides are extremely rapid based on the popular landslide classification scheme, so that moves typically at velocities of more than some meters per second. But as you can see here, that are not anticipated by detectable precursory displacements. We can say that they occur rockfall as are a representative of this type of phenomena. They occur basically suddenly. They cannot be predicted. And these kind of phenomena, needless to say, they are very frequent, both spatially and temporally, and mostly affect mountainous areas and specifically infrastructures such as and transportation corridors such as highways and railways. And roads and highways and roads in general are the main probably field of application of this particular Doppler radar technique. And I will show you a practical example of it in just a minute. First of all, again, I'm not a physicist, so I'm not able to get into the technical specifics of the technique, but I can just give you an overview of the general principle of the technique.
Oh, thank you very much. Thank you very much. Yeah.
There's an open microphone, sorry.
I'm attending one webinar. Yeah, mic off.
Someone has an open microphone, sorry.
Yeah, I think it's closed now.
Okay.
Sorry, please go ahead.
Yeah. And so as the name suggests, the Doppler radar doesn't work with the phase information, but the frequency information of the backscattered signal. So the principle of the technique is that, again, a radar unit continuously transmits a microwave towards the monitor, the slope that one wishes to monitor, and then receives the backscattered signal, and by means of confusion matrices and other kind of algorithms, this signal is analyzed mainly in terms of frequency. And so if the returning signal has the same frequency of the transmitted signal, then the instrument can assess that there is no ongoing rockfall along the slope. So again, no frequency shift, so no rockfall. Then a rockfall may start at some point, and this will cause a shift in the frequency of the returning signal. And this, of course, can be interpreted as a Doppler effect, and the instrument detects almost basically in real time that there is an ongoing rockfall. It is capable of detecting a rockfall within a couple of seconds from its triggering. And so this information, when the instrument knows that there is a rockfall ongoing along the slope, the instrument, it is usually connected to alarm devices such as traffic lights in the case of, for example, of a section of road that is at risk of rockfalls, and therefore it can trigger the red lights of these traffic lights. And this allows vehicles that may be traveling along the road to stop and remain outside of the area at risk for as long as the rockfall is ongoing. And also it gives enough time for vehicles that were in between the traffic lights when the rockfall started. It gives them the time to evacuate the area at risk, pending that they do not stop, of course, in this section. The Doppler radar is, let's say, more practical than interferometric radar, in the sense that it doesn't need mobile parts. It's just a couple of units installed on a fixed pole that is grounded, that is fixed to the ground. And it is composed of a survey unit, of a compact survey unit that is in charge of transmitting and receiving the microwave information, and a control unit that do all the processing and analysis to determine whether there is a rockfall ongoing or not. And that is also in charge of uploading data on cloud portals and send alerts notification via SMS and email, and also to activate local alerts like traffic lights, but also, for example, alarm horns or sirens or mechanical barriers. And the important part of the very important feature of the instrument that is probably separates it from other previous iterations is that there is a GNSS the survey unit is integrated with a GNSS component. And this GNSS component is exploited to not only detect whether a rockfall is ongoing or not along the slope, but also to track it, meaning to track the rockfall propagation trajectory. So to have a fully three-dimensional spatial information of the fall trajectory. And so this is, we will see why this is very important. So just, it's probably better to let you to demonstrate how the instrument works to describe a real case, very recent real case example that was of a monitoring campaign that was undertaken at the Ruinon landslide, which is a very large and popular and famous landslide in the central Italian Alps. This is actually a rock slide, which is very large, almost 30 million cubic meters. And it is quite complex because it is nested within a very much larger deep-seated gravitational slope deformation. You can see here it's just this small block of this large and stable slope. But the rock slide itself can be very schematically represented in this cross-section. It is composed of an upper layer of very incoherent debris and disaggregated substrate that moves at velocities much faster than the lower layer, which is heavily fractured and disturbed, but still solid, let's say, substrate composed of metamorphic phyllite rocks. And the critical part of it is that this rock slide is located just above a road, a very important road, which is represented with the red line here. And this road connects two popular tourist towns in the Italian Alps. One is Bormio downstream, and the other one is Santa Caterina in Valfurva upstream. It is a very narrow valley, so there is no other path to reach Santa Caterina in Valfurva. And also this town during the winter can only be accessed through this road. So you can understand why it is critical to keep this road open. We also had a ground-based interferometric radar monitoring in place. We have been having that for more than a decade now. And this instrument showed that the displacements of the lower part of the slope, especially the part where the debris was more developed, the upper layer of debris was developed, were increasingly following an increasing trend, especially in the summer 2019, due to large precipitation and rapid snow melt occurring at a higher elevation. There was like a very important flow of underground water that reached the landslide area, and this caused dramatic increases of landslide velocities in the lower part of the slope, up to more than 1 meter per day on a daily basis. So this is an image, a frontal image of the most critical slope sector. As you see, the debris traveling at the velocities of meters per day downslope, this lobe of debris. And here you have a time-lapse imagery of the movement of these debris. Now, this, you may say, it's not necessarily critical for the slope, for the road in the valley floor. We also had, there was also a protection embankment here, protecting the road. So you may say, okay, that's not necessarily a big problem for the road, but the problem was that this debris was actually enclosing very, very large boulders up to sizes of several tens up to hundreds of cubic meters. And the continuous movement of the slope allowed some of these boulders to daylight, and also there was the chance that these large boulders could be destabilized and released from the debris and then generate a rockfall. And of course, there's no rockfall barrier or embankment that can protect you from boulders ranging in size up to hundreds of cubic meters. And this is what actually occurred in the summer of 2019, when the 70 cubic meter rockfall smashed occurred and smashed through the protection embankment and reached the road, luckily causing no casualties because nobody was traveling along the road at the time. So the following year, in the spring of 2020, we decided to install the instrument, and was actually the first application, at least in Italy, of this instrument. So here you have a schematic map of the system configuration and of the configuration of the real-time alert system, along with an actual image of the instrument and the field of view of the instrument. So you have the instrument here on the opposite side of the valley, on the opposite valley side. And we installed 2 traffic lights, one for each, one at each end of the protection embankment, which is represented by this yellow line here. And so the traffic lights, by means of fiber optic cables, were connected to the radar unit that was then able to control them automatically without the intervention of the user. Along with the radar unit, we also implemented a very detailed video surveillance system, so that anytime there was a rockfall event along the slope, we were able to actually check the images and see what happened. And this is important for the operational management of the road. And we decided to distinguish between 2 cases for the automatic management of the road based on Doppler radar monitoring, because there were basically 2 scenarios. Remember that this is a road that must remain open by at most. Sorry. This is a road that must remain open as much as possible. Okay, so the problem is that when you have the onset of a rockfall, you cannot know for sure whether this is going to reach the road or not. It may stop along the slope and therefore cause no threat to vehicles, but it may be large enough to reach the road. So we decided to distinguish between 2 cases. In case 1, the rockfall remains within the so-called region of interest, meaning you have the onset of rockfall here, and the rockfall stops still along the slope within the so-called region of interest. In this case, the traffic lights are automatically turned to red as soon as the rockfall starts. But then when the instrument is able to see that it stops still along the slope, so there is no longer a threat to vehicles, the traffic lights are automatically switched back to green at the end of the event. This is useful because most of the rockfalls occurring at Rinon were this case 1. So we could basically keep the road open for most of the times. In the second case, the rockfalls entered the so-called danger zone. What is the danger zone? It's basically the area of the monitored part of the slope that includes the road and the very, very toe of the slope, okay? Because of course, if the rockfall reaches the toe of the slope and hits the and has an impact with the protection embankment, we cannot know for sure whether the embankment was able to keep it in check or whether this was damaged and perhaps even the rockfall had reached the road. So in the second case, at the end of the event, the radar unit would order the traffic lights to remain red, and the only way to turn them back to green was by means of a manual intervention and check of an operator that switches them back to green. This could have been done both on site by means of a simple button, but also critically by means of a remote platform where the data were uploaded and the images also were uploaded. So the user was in charge of managing the road was able to, okay, there has been an alarm, a rockfall has reached the danger zone, I'm going to check the images from the various webcams that had been installed, and if I can assess that there's no threat and no damage to the road, then I'm able to switch the traffic lights back to green from remote, from my office computer. Okay, so this also was very critical in maximizing the times that the road was open. So I think it's beneficial to give you a couple of examples of the probably two major rockfalls that occurred during the monitoring period. This one was a 5 cubic meter rockfall that occurred on 12 September 2020, and that caused the first that reached the danger zone. And here you see the output of the Doppler, the final output of the Doppler radar, which is a heat map, basically, which is colored in tones of red, and where the darker red means that the intensity of red is proportional to the momentum of the rock size. So, and this momentum is of course related to the intensity of the Doppler effect. And so from this map here, you can see where the rockfall occurred. And here you have the list of messages that were sent to users during the event. I also want to show you this second event that occurred a bit later on 1 October 2020. This is very interesting because you can see was a roughly 2 cubic meter rockfall that started upslope here. And at some point, you see there was this splitted, okay, into two separate rockfalls, one going here and one going in this other direction. And this was actually captured by the instrument. You see the heat map that starts as a single trajectory, and then there is a bifurcation in the lower part of the slope, as actually occurred. So this, of course, I think it's a good example of the powerful characteristics of this instrument. So to conclude my presentation, I've shown you mostly the practical application of the Doppler radar or rockfall or Doppler-based rockfall radar. But of course, there is also, I think, scientific implications that will be explored in the future that are very important. One, above all, is the fact that the instrument is capable of giving the user objective rockfall runout data in terms of travel path and travel velocity, okay, and velocity of the rockfall. So these information can then be used for calibration of rockfall runout simulations, and this can be a robust base upon which to calibrate forward modeling of rockfall runout. Okay, so I think this is the main application that has the potential of being explored in the future. And the second application, scientific application, is that again, these objective data, we now know for sure when and where rockfalls can have occurred at a certain site. And these, therefore, are objective data upon which to calibrate, to perform a quantitative analysis of rockfall frequency, size, and triggers. Of course, we are talking about these are going to be site-specific, at least initially, site-specific analysis. But as we collect more data, I think we can gather enough information to also make conclusions about rockfall processes in general. And really, just to sum up the presentation, as the final slide of my presentation, we see here the classes of landslide velocities and a list of very general landslide types. You can see that landslides that have undergo catastrophic failure undergo precursory displacements that are typically from very slow to moderate, and that can be very well captured by ground-based interferometry. On the other hand, you have sudden landslides like rockfalls or debris or shallow landslides like debris flows that are suddenly triggered and immediately travel very rapidly or extremely rapidly, more often extremely rapidly. And these can be well covered by Doppler radar. There is still some kind of middle ground, mostly in the rapid class, which is mostly pertinent to earth flows, which are soil slides that usually move slowly to moderately, but can experience surges during wet periods that usually are in the order of meters per hour. And this kind of velocity interval is too high for the ground-based interferometer, but still too low for the Doppler radar. So this is still maybe the only hole that we need to address, the only gap that we need to address in terms of landslide displacement monitoring. So thank you for your attention. I'll like to conclude with a picture of the traffic lights installed at the renowned rockslide. Thank you again for your attention.
Thanks to you, Tommaso, for teaching us about such an innovative technique, a very groundbreaking technique. I'm sure it was interesting for our audience, both from Italy and from India. So again, thank you for this nice presentation. There is plenty of time for some question, if there is some from the audience. Any questions? Okay, if there are no questions, I have some curiosity.
Yes.
Okay,
Buongiorno,
please
can you
go
hear
ahead.
me?
Yeah.
Yes. I am Taraka from University of Siena. How much is the cost of this, let's say, this setup as a whole?
Yeah, probably I should have listed these in the downsides of the instrumentation. Of course, these are the most advanced, probably the most advanced monitoring techniques, but of course, they are also the most expensive ones. And probably the ground-based radar now, the price of it is between, usually these instruments are rented, not it's not convenient to purchase them, but it's more convenient to rent them, and the rent cost is about ranges for the interferometric radar between 50,000 to 100,000 euros a year, and the Doppler radar maybe even a little bit more, because it's also more complicated with the interaction with the alarm devices. So this is going to come at between 100 and 150,000 euros per year.
Okay, so
of course, this is the first year of monitoring that also includes installation. So after the first year, the second year, the rent cost will be a bit lower, but still in the range of several thousands of euros per year.
Okay. Thank you.
It's nice because I had exactly the same curiosity about the price. Hopefully this is, we are at the early stage of implementation. So maybe in the next few years, the prices will go down, hopefully, I don't know. And so from the application point of view, I think this technique can be applied only if we have big fundings, such as big projects, or maybe high elements, high risk in very valuable elements, right?
Yeah, that's also a reason. Probably I show you two case example, as you said, that where the elements at risk were high value, and therefore the importance of safety, and in the case of the sanctuary Gallivage, and in the case of Ruinon, also the need to keep that road open was the importance of those elements was higher than the costs involved in the process.
Sure, of course. And so another implication is, I think, that you use them with for national scale emergencies, or with the national department, not I mean, local authorities probably are not able to afford the cost. Is that
Yeah,
right?
yeah, exactly. Small landslides that may affect low elements of low importance, or landslides that are not difficult to characterize in terms of kinematic and displacement behavior. Of course, they do not warrant such a big investment. Usually for
Okay.
large phenomena that may have big impact on the local communities.
Okay. Other questions from the public? If not, I have one last curiosity. Did you ever had false alarms caused by something else other than rock falls, like, I don't know, animals or other things?
Yeah, you mean for the Doppler radar, I guess.
Yeah.
So actually, it's quite rare to have false alarms. They are mostly related to, especially in alpine regions, to weather fronts moving very rapidly. So during, for example, summer thunderstorms. This is not necessarily a bad thing. I mean, if you have a false alarm during a very heavy rainfall, even if actually rockfall is not occurring, but it may occur soon, so it's not so bad to have a false alarm in these kind of situations, and can be easily seen from remote, as I mentioned. So if it's easy to see a false alarm and to interpret it as such. And as far as other kind of false alarms, not really. For example, animals are usually too small or too slow to trigger an alarm, and also the algorithms that analyze the returning signal are usually are sophisticated enough to be able to distinguish a consistent rockfall path to a random travel path of an animal or other kind of objects that are not actually moving downslope, such as a rockfall.
Okay, thank you. We have a question from the chat. I don't know if you can read it. Otherwise, I can read it for you. Can we go for artificial intelligence techniques such as image processing that maybe can reduce the costs?
Yeah, I think in theory, yes. But again, you have to keep in mind that these are commercially available instruments. So at least I'm not aware of prototypes that have been developed for personal use of academic institutions or other kind of research institutions. So we have to basically adhere what the market can offer us, right? So as long as the developers and the companies that distribute these instruments do not perform such developments, I don't think there is a practical, at least at the moment, a practical way to implement those kind of tests and updates.
Yeah, then I'm sure artificial intelligence is implemented inside maybe the processors inside the instrument.
Yeah, but as I said,
however, it's good because there is plenty of opportunities for further researches.
Yeah,
there is a lot of researches.
Working with this, yeah.
Yeah. Okay. Thank you again, Tommaso. If we are done with the questions, I could move to the next speaker, which is Dr. Deepak Manjunath. I apologize for any errors of pronunciation.
You're right. Spot on.
Thank you. Just a brief introduction. He's an engineer, he's the head engineering operations at Terre Armée, India, and he holds a PhD in geotechnical engineering from the University of Missouri, Columbia. Deepak has more than 18 years of experience in the geotechnical field, gained both in the USA and in India, with several and very different cases of study. So I think we can start. Deepak, please go ahead.
Okay.
We can.
Okay.
Everything seems in order, so you can go.
Okay. So firstly, I would like to, thank you for giving me and giving the company this opportunity to basically talk about this topic. The presentation so far have been really interesting, and got to know how the monitoring aspect really works. What we are going to present to you today is slightly moving out of the remote sensing aspect, and we're going to cover a technology that was used to mitigate a landslide site that we had in Thin area. So without much delay, I would like to step into it. So I see that my slides are not changing. Just give me a second. Okay, can you see my slides?
Yes, we can.
Yes.
Yeah, okay, fine. So I'll basically start by giving you an introduction of the project site. So basically what you are seeing on the screen here is basically a snippet of a newspaper shot from September 2011. So basically there was a really large earthquake of a magnitude 6.9 on the Richter scale, which basically took place on the 18th of September 2011 in the region close to Sikkim. So now this huge seismic event basically triggered several landslides, out of which the most critical one basically took place in the Darjeeling region in West Bengal. The site is called Thin area, and it is basically situated in the seismic zone 4. Now, it's basically interesting is the fact that this particular landslide gained a lot of interest and a lot of interest and a lot of push to basically have the slide zones stabilized, especially because you can see the portion that I've basically marked in yellow is basically the landslide zone was basically below a UNESCO World Heritage Site, which is basically the Darjeeling Himalayan Railway Workshop. So we were basically tasked with the responsibility of stabilizing the slide, rehabilitation, right? So just like to flash on screen, the very relevant paper which has been published by Dr. Satyam. This is a really interesting paper that basically talks regarding the seismic setting of the region in which this particular earthquake took place, and also which triggered this large landslide. So basically what you would need to know is, the kind of soil and the rock profile which was predominant. So basically the site was characterized mostly by colluvium and residual kind of soil. There were also bands of coal and peat, varying in thickness from 0 to up to around 7 meters in thickness. And at the bottom of the slide zone, you had, basically fragmented sandstone, which was basically exposed. And right at the bottom of the landslide was a flowing stream in which the flow had basically surged following the seismic event. So basically, we're talking about a seismically induced landslide. And we are just going to show you the remedial measures which were basically implemented. So let me just start by showing you the site locations. So we spoke about the major landslide, right? So I'm just showing you here a Google snapshot. So we stabilized 3 slide zones following the earthquake. So the major slide was the one which I'm showing here with my pointer. The stabilized height was 102.8 meters. There were also 2 relatively smaller slides which were stabilized. The slide 1, on which I'm showing my cursor right now, had a total height of 35 meters. And one more slide, which was slide number 3, as we like to call it, had a retention height of close to 30 meters. Now, these are, the photographs of the 3 slides, which we call S1, S2, and S3. So just for clarity, this is slide number 1, which had a height of 35 meters. This is slide number 3, which had a height of close to 30 meters. And this is the huge one, which had a height exceeding 100 meters, right? So basically, what was the objective was the number 1 part was to stabilize the landslide zone. So we had to provide a solution for landslide protection for S1, S2, and S3. What was also required is the widening of the road. So when the landslide took place, a portion of the road caved in. So to basically plan for the future, part of the objective of the project was to stabilize the slide and also to widen the road, which was going to come on top of the stabilized structure. We, of course, took place that the construction was executed with safety. Safety is a huge concern here because we're talking of a slide that basically took place and of a huge height. So it was very, very crucial for us to ensure that all the construction work took place with safety. The 4th, which was mainly a very, very important factor, was the amount of soil that was required to be filled. So you would not know what I'm talking of right now, but once I show you the solution, you would be able to appreciate that the quantity of excavation and filling was extremely small. And the solution that was provided made sure that the natural resources would be preserved and the quantity of filling material was kept to minimum. The 5th important part, like we know, is most landslides. Of course, the landslides are triggered by, seismic events. But what basically happens is, the seismic events basically also result in an increase in the pore pressure. And hence, it's basically extremely important to flush the landslide zone of any water. So it was extremely important to ensure proper surface drainage system which basically would ensure that there was no scope for pressures to build up, right? So these were the 5 objectives on which we kind of worked out the solution. So the proposed solution or the system which was implemented here is called a TerraLink system. I will show you why it's called TerraLink. Before I go into the specifics, I just want to update you why this kind of a system is used. So the traditional retraining walls, which are basically known as the traditional reinforced soil structures, they basically require that the base width should not be smaller than 0.4 into h. 0.4 into the height of the structure is applicable when your cut slope or the exposed slope is basically characterized of rock. If you have a soil slope, the requirement is that the base width I am speaking of is the width of the reinforcements which are going to be used. So if it's rock, we need 0.4. So the base width here has to be 0.4 into the height of the structure. And in case the slope here is characterized by soil, we require the base width to be at least 0.7 into h. What we had at Daria following the landslide was, we had a base width of basically close to around 4 to 5 meters. And 4 to 5 meters, when basically compared with the height of the structure, which was close to 100 meters, was basically 0.005 h, right? So, so we basically proposed this system, which is a reinforced soil system, which combines the use of soil nails, so the soil nails are basically used to stabilize the exposed slope, which is following the landslide. And following this stabilization, because the road width had to be increased, we had to go with a composite reinforced soil slope, which basically had geosynthetic strap kind of reinforcements, which basically ran from the facing up to the nails. We also installed cable anchors here, which basically ensured the compound stability of the complete structure. So here is a slide that basically shows you real close-up of the kind of solution that was implemented. The kind of solution that was implemented is basically shown on the left side, wherein if you assume that the slope, the exposed face following the landslide, we basically stabilize the slope with nailing, and at the facing to basically have space to basically increase the road width, we had a welded mesh facing. Behind the welded mesh facing, we had 400 mm thick zone, which had the facing stones. The facing stones, as I will explain in the following slides, basically served the purpose of providing an aesthetic finish and also ensured proper drainage at the face. And the reinforcing strips, which I spoke of, the geosynthetic reinforcing strips, ran between the facing element and these soil nails here. So you had these strips going back and forth, back and forth. The specialty of this system is that the reinforcing strips are basically connected with the soil nails. We will show you how. Okay. So now we'll get into stabilization and widening at structure 2, which had a height of around 100 meters. So this was the situation just after the landslide, and the system looked like this once the rehabilitation was completed. So what you're looking at here is a model of the world's tallest reinforced earth structure so far at 102.8 meters. Now we just compare, what could have been the solutions, right? So, like I spoke, whatever you have on the left side here is a conventional reinforced soil structure, wherein the base width is, basically 0.7 times h. Here it is not 0.7 h, it is basically 0.4 h, because the height of the rectified solution would have been close to 100 meters, but the 0.7 h rule was not applicable here because you had the cut slope being characterized by rock. Now, compared to the conventional reinforced soil solution, here is what we have proposed, which is basically called composite reinforced soil solution. And what is striking here is that the consumption of the soil. So basically what we have here is the reinforcements, the geosynthetic reinforcements need to be held together by soil. So the construction sequence is that you have alternative layers of compacted soil and geosynthetic reinforcement straps, which are basically shown over here. So the advantage of the Terraling kind of a solution is the amount of soil which would be used for filling is extremely small when compared to the quantity of soil which is going to be used in a conventional reinforced soil system. Now, and also what you can see here is the nailing system, which has gone to stabilize the slope. When the space that is occupied by the structure is extremely small, then the requirement for compaction equipment is also smaller, and also we have saved a lot on the fuel which is basically consumed in transporting the fill soil from the source up to the site of construction of the structure. Now I move on. So here is just an animation that is basically showing the reduction in the cross-sectional area of both the solutions. So we come to the design concept here. So when we are basically ensuring that the solution is safe in both global and local stability, we have global checks, and we also perform compound stability checks. There is a separate procedure for the design of the ground anchors, which have been installed here. Ground anchors are basically cable anchors. So the cable anchors have been also installed here. And we check for the internal stability, where we check the straps are safe in rupture as well as pull out. And the compound system's performance was validated by finite element method modeling. So I'm not going to go too much into the specifics of what the codal provisions say, but this just kind of gives you a visual experience of, the kind of failures surfaces which are basically examined. So this basically constitutes a reinforced soil slope, which is not a reinforced soil wall. It's a slope which has a face angle of 70 degrees. And so since it's a slope, the checks which are basically required are basically limit equilibrium checks, wherein we check for rotational stability. What I also have here are the load factors and the reduction factors, which can be used in the design of the complete system. For the global stability, the target factors of safety without seismic loading is 1.3, and in the seismic case, the targeted factor of safety is 1.1. I have a few snapshots of the stability analysis which was carried out. These are for various drainages on the rehabilitated landslide site. So what is presented here is the critical circle, and basically we are seeing that the factors of safety that we have are much more than the required factors of safety of 1.3 in static. Here is one more snapshot of the slope stability circle in seismic loading, where the targeted factor of safety was 1.1 and we had a factor of safety of 1.3. We keep moving on here, and here is where we need to, really talk of how the phreatic surface is considered in the stability analysis. So what you are seeing here is a snapshot of the global stability check, which has been performed in the presence of the phreatic line. So one of the characteristics of the landslide site was that there was presence of perennial streams or springs. So the perennial springs usually found an exit at the exposed surface of the landslide. Hence, the phreatic surface should have looked going, like this and basically coming out of the slope surface. Why it has been considered here is because we have managed to push the phreatic surface back through the use of drainage pipes. So we had perforated pipes, which basically extended almost 20 to 30 meters within the landslide surface, which was basically exposed. So that is the reason why the shape of the phreatic line here is not as you would usually expect it to be. The factors of safety that we had with the phreatic line in static was also in excess of 1.3. We also checked it in seismic, and it was exceeding 1.1. I don't have the slide here, This is once more slope stability checks, which were performed for, the smaller structure, which had a height of 30 meters. So this is just to show you that, the required factors of safety were met and checked. Like I said in my previous slides, we also checked for deformation at the face by basically performing finite element method analysis. We've used these software FLAC, which is basically a commercial software, and basically you are seeing the contours of the deformation. As you would see, we have basically performed the finite element method analysis for all the three structures, and the expected deformation is much lesser than the limit. It basically ensures that the structure is fine and serviceability condition. Now we talk a little bit regarding the drainage system. We had a very intricate system of drainage, which included surface as well as subsurface drainage. So what you're seeing on the sides is basically a drop and guide structure, which is basically meant to channelize the water by dissipating the hydraulic energy, which is basically generated by falling water. So these are a series of steps. So it's basically a step weir. We would like to call it a drop and guide structure. So we have these structures on both the ends of the structure. And we have the surface drains, which go in a zigzag pattern to channelize the water from the edge of the road here up to the bottom. And you would see that the slope of the drains, which are basically shown by the black arrows here, basically channelize the water into the drop and guide system here at various points, so that the water, or the water that is basically coming out of this system is channelized properly up to the bottom of the slope. Here is once again a cross section that shows details of the subsurface drainage system which has been provided. So what you see here marked in blue is basically a chimney drain. Okay? You have a chimney drain that basically goes down from the top of the structure and basically spans the complete height. And the chimney drains have been made by basically placing 100 mm to 200 mm sized boulders. These boulders have been selected and basically placed on site by hand, so that the composition and the grain size is controlled. What you would also see here is that the 400 mm thick placing of stones at the facing. So the 400 mm thick stones, they basically make sure that if you have any water that basically comes down the reinforced soil surface and not captured by the chimney drain or the subsurface drainage system, is basically captured at the face by this 400 mm thick stone pitching, and it is basically channelized outside the structure, and it basically flows down to the base, right? So here are a few more slides which are basically showing the intricacy of the drainage system that was conceptualized and executed. Here are a few photographs which are showing various phases of the construction. So the construction sequence, since the landslide had taken place, and the landslide, the cut slope was basically exposed. So basically, we had to follow an installation sequence from the bottom to the top. So what you are seeing here is basically the excavation works in progress. So the excavation sequence basically started at the top of this structure, and it basically had various phases of scaling and basically earthworks, and we worked our way from the top of the slide to the bottom, where we had to start the construction of the structure, the rehabilitated structure, if you will. Following the preparation of the slope, the nailing works were basically executed. The nailing was performed from bottom to top. So the excavation took place from the top to the bottom, and the installation of the nails took place from the bottom up to the top. So here are a few schematics and a few photographs showing how the execution was performed. What you are seeing here is machines which are basically drill rigs are performing nailing works here. So this was basically at the bottom, and this was way back in 2017. Now we talk a bit regarding the connection, the way the geosynthetic straps are connected to the nails. So basically what we have here is the dotted line here can be considered as the face of the slope, which was stabilized. So the construction sequence was, of course, we would first place a layer of non-woven geotextile, and followed by placement of a welded mesh. Once the welded mesh was placed, we carried out the soil nailing works. And the welded mesh and the non-woven geotextile was basically secured in place by bearing plates, which you can see here as well. And we had a specific connection system which basically enabled the straps to be connected with the nail. So you could call the para plug and the U hook, and also we have a separate component called the horseshoe, which basically goes in a U shape from here to here. So the straps go from the facing up to the nail through the shoe, and it goes back and forth between the facing and the nails. One of the key things that had to be taken care of is the bond strength. We had to basically ensure that what the bond strength was for the nails. So this was ensured by conducting pull-out tests. So on the right side, you will see the complete schematic for the setup of the equipment for the pull-out test. So pull-out test, for those who don't know, is basically we install a pressed nail at this height, and we grout it. And following grouting, we basically have a concrete padding at the face of the slope to have the reaction, and we use a load cell which is connected to the nail through a system called a ram. So the load cell exerts pressure on the ram, and hence the ram basically pulls the nail, tries to pull the nail um, uh, uh, out of the soil. So in the pull-out test, what we are trying to do is basically trying to calculate the total, the maximum force that is required to pull out the nail and the grout from the surrounding ground profile. So the pull-out tests were basically conducted to estimate the bond strength, which has to be considered in the design. What we are showing you here is a photograph of, the partially stabilized slope. There are a few photographs to follow, which are basically showing the stage-wise execution of the stabilization works. So far we have basically spoken of how the exposed slope surface after the landslide was stabilized. So these are a few more photographs which basically show the sequence of construction. So somewhere in between this photograph here and this photograph here, we are showing you that the bottommost tier of the reinforced soil slope has basically been constructed here. So this once again is the facing and the straps portion of the construction, which is shown here. This is a close-up. So basically here what you have is the stabilized soil slope went like this, and here you have a system of welded mesh and a facing stone and a reinforcing strap and soil, which basically went from here to the surface of the cut slope. So the same process was repeated. What you are seeing here is the concrete blocks that have been installed to enable the post tensioning of the cable anchors, which were basically installed. So the cable anchors basically sandwiched the reinforced soil system between the face that is here. So the cable anchors sandwiched the face of the reinforced soil system and the cut slope surface, which was basically behind the wall. Here is a video which I would like to share, which is going to be really quick. This is basically a drone shot that basically takes you from the bottom of the structure up to the top. So you're basically seeing the complete 102.8 meters, except that at the time that the video was taken, there was maybe 4 or 5 meters of construction that was pending. What you would see here is, the zigzag surface terrain, which was shown in the previous slide. So any water that you have, which basically runs off from, the road, or which is basically collected during rainfall, is basically channelized in a slope fashion and basically goes in a zigzag way and basically goes all the way to the bottom. This is a photograph of the completed structure. The previous video showed you what it looked like when there was basically 4 or 5 meters of execution pending. Here you have a photograph of the complete structure. We also have a few photographs for you for the structure 1, which was close to 35 meters height. The solution used was exactly the same, except that we did not use any cable anchors here. There were no cable anchors in S1 and S3 because the stresses on the wall were not so high, and hence there was no requirement for cable anchors. I think that's all I had for you. I am open to answer any queries that you may have. Thank you very much.
And thanks to you for this very interesting presentation.
Hello.
So there is...
Yes,
Hello,
Mr.
Dr.
Ravi.
Deepak.
Yeah, yes.
Yeah, good,
Hi, hi.
good afternoon, good evening. How are you?
Good evening, sir. Really good to hear from you.
Yeah.
Yeah.
It is nice to hear from you about the project where we have jointly worked together.
Right, sir. Right. That is what I.
Fantastic. Your presentation was truly fantastic and comprehensive. And this is just for information to all that actually myself, I am Engineer Avik Kumar Mandal, actually from Lee Associates South Asia Private Limited. And our organization did the DPR conceptualization of the project on behalf of Ministry of Road Transport and Highways, NH Wing, West Bengal PWD in 2015-16. After that, it was constructed on design-build basis, and the design was further verified and validated by this proprietary material of Terre Army, which was executed from 2017 to 20. Am I correct, Dr. Manjunath?
Yes, sir. Yes. You are.
Yeah. So it is a fantastic presentation. You have covered all three. And for the information to all, and I think Dr. Deepak, you also might be definitely knowing, we have written one paper which was published on year before last year IGC, the NIT Trichy conference.
Yeah, right.
Yeah, where Mr. Atanu Adhikari has also the co-authored along with me, and he has given very detailed depiction of the construction and design validation during construction stage. An initial part of the paper was drafted by me mostly, and the paper was published in NIT Trichy IGC conference. But that paper was based on the S1, means
S1.
the moderate height of slope, not the big one, which is a gigantic and truly comprehensive and exhaustive. It is a valley slope building with a reinforced hybrid technology. The one thing is that, Dr. Deepak and to all actually, even though in DPR stage, we propose lots of instrumentation for monitoring of the slope, particularly in post-construction behavior, with all these piezometers, strain gauges, inclinometers, but because of paucity of funds and all these things, finally, those things have not been installed. But however, I think what we came to know from the authority that day-to-day monitoring through normal survey equipments of the slope is going on, and till date the slope is perfectly functioning.
Yeah, sir, it is fine. It's fine.
Intended purpose for which it was designed and constructed there.
Right.
Thank you. This was my just observation to the presentation. It was a very nice and very exhaustive and comprehensive talk. Nice to see you. Thank you.
Thank you very much, sir. Thank you very much.
Any other comments from the audience?
It's I mean, flag software you have been used here. So is it finite difference method? I think so. Is it right or I'm wrong? Just want to confirm.
Sir, can you repeat, sir? I was not able to hear you.
Yeah, you have mentioned that flag it's a finite element method.
Finite element method. Yes.
I believe that it's maybe a finite difference method.
You are right. FLAC is basically finite difference. We also had we also performed it in Flaxis, which is basically finite element. So
yeah,
yes,
it was on Flaxis.
You're right.
Okay, thank you.
Any other comments or questions?
Yeah, I got one question to be made.
Please go ahead.
What is the scope of soil investigation you had to evaluate the initial set of parameters for as an input data?
Yeah, sir. So basically, we had a geologic mapping which was performed, and like I said, the kind of soil that we observed at the site varied from colluvium and residual soil at the top to weathered sandstone at the bottom. We also had a bed of, say, peat, which was observed. So basically, we considered friction angle varying between 32 and 36 based on the kind of profile which we had. So we had an extensive geotechnical and geotechnical investigation, and also a geologic mapping which was performed. I do not have the slide where we have shown the boreholes which were basically executed. I think we had a total of 7 locations where we had 3 locations at the top of the slide, 2 locations in the middle, and there was maybe 2 more locations at the bottom. So we have captured the complete height range of the slide so that we could have a proper characterization.
Any dilatometer test you have done in that, forget the lateral forces?
Dilatometer, no, sir. No.
You're in neither pressure meter. Okay.
No, sir. No.
Any specific in situ test which you did on this? Like only as you depended on SPT, or you had any other thing?
No. We had a rock mass classification,
okay,
which was performed, and this was basically part of the geologic mapping. For the bearing capacity, we basically used the frictional properties. So we used the rock lab wherein we derive the shear strength parameters based on the jointing and the rock mass properties which we had from the geologic mapping. So it was basically a reverse modeling combined and validated by the geotechnical investigation reports.
Oh, good. Thank you.
Yeah, I have one more query. Like, is there any kinematic analysis done before doing mitigation measures?
I wouldn't say parametric, but I would say sensitivity. We considered various combinations of shear parameters, and we used the worst case.
No, sorry. It's a kinematic. Is there done any kinematic analysis, like planar value or any like that analysis done?
Sir, we have not checked for planar because the landslide has taken place, right? And basically, but what we made sure is when we checked the potential failures surfaces, we made sure to basically check what is the factor of safety with a slip plane which was parallel, or which was basically at the interface of the reinforced soil zone and the exposed slopes surface. Because we had nailing and cable anchors and also geosynthetic straps, we found that the factors of safety on a planar surface was extremely high.
Okay.
No, but for designing the soil nailing, you said that it is a rock mass classification. Am I right? Hello?
Yes, rock mass classification and also the bond strength. So we basically, so we basically need to ensure that the nail is safe in both rupture and pull out, and hence we had to know what the bond strength was. So the bond strength was the main characterization which was required, right? So,
Now, what sort of a grout you used? Any grouting was done there?
yeah, sir. So basically, the procedure was to have a drill hole and insert the nail and have grouting performed. So the water cement ratio of the grout was close to 0.4, and the compressive strength after 28 days was close to 25 megapascals.
Okay. Good. Thank you.
Sure, sir. Thank you.
Hello?
Yes.
Can you hear me? Yes.
Yeah.
So first of all, congratulations for this project, because it's very challenging.
Thank you.
But I would like to know if it was possible to fill the geogrids with earth rather than stones to reduce the landscape impact. You know, at least the most external part of the grids.
Yeah. So we had rock facing at the front, which was basically for a width of 400 millimeters. Following the 400 millimeter facing, we had soil.
And I mean the external part of the grids of the reinforced grid. Usually we use the technique with landfill. I mean, filling with earth in order to let the roots of vegetation to grow and to reduce then the impact on the landscape. That's what I was asking.
Yeah.
So is it?
This was a possibility, but basically what happens is you would appreciate that the slope is extremely steep. So you are having a slope angle close to 70 degrees. And when your slope angle is so steep, usually the chance for vegetation to grow is very, very less. And hence we did not want to take the chance. So we have basically gone ahead with a stone filling. And if I'm not wrong, the requirement from the government officials was also that they required a stone facing to make sure that the rectified solution and the structure had a aesthetic look. So that is the reason stone facing was used. But yes, there was also an option for using vegetated facing. Yes. You're right.
Thank you. Thank you.
What was the anchor capacity, sir?
Sir?
What was your soil nailing capacity of the nail?
Yeah, sir. So we used FE 670 by 800. So the yield strength was 670 megapascals. And the capacity of the cable anchor was around 47 metric tons.
Good. Okay. Perhaps the fixed length was much lesser, or it was quite large because you have put it into the rock, no?
Yes, sir. So the cable anchors extended for up to, say, 50 meters at least.
Achha. Yeah. Okay.
Any other comments? If not, I will move to the next speaker. But first, I would like to thank again you for this.
Thank you very much.
Very nice presentation, very complete, very challenging the work, and it's nice because we were talking about research, then this is more about actual implementations to solve the problems of landslide risk. And now we move back again to research, applied research, with Emanuele Incieri. He's the next speaker. Emanuele is a tenure-track researcher at the University of Florence. He is the holder of the geotechnics course at the University of Florence. His research interests are mainly focused on landslide forecasting and monitoring, especially through interferometric techniques. In the recent years, however, he extended his research field to the application also of geotechnical techniques for monitoring, characterization, and analysis of cultural heritage sites, with the aim of assessing the risk of collapse of stone elements from historical buildings in Florence, in the city of Florence, and all over Italy. Basically, I think he's treating ancient buildings like cliffs with the problem of rockfalls, more or less. And so, Emanuele, are you online? Yes, I can see you.
Can you hear me?
Yeah. Yes, we can hear you. You can share your screen.
Okay. Okay. You should be able to see the presentation, right?
Yes, but we see next, not the full screen mode. We see your
Okay,
screen
I need to change.
with the notes and the
Yeah,
next slide.
I need to change.
Yeah, sure. Take your time.
Okay,
We
now?
are a little bit ahead of the schedule. Yeah, now is perfect.
Okay. Okay.
Okay, we can go.
Okay, thank you. So, in my speech, I will talk about landslide forecasting and early warning. We have already seen today and yesterday some presentations about this topic, but I will focus more on forecasting and early warning made using displacement data, so made at the slope scale. We can think about early warning as a sort of a third line of defense against landslides, whereas the first line can be represented by the urban planning. If we have a correct urban planning, we can mostly, in many occurrences, we can manage landslides and reduce risk significantly. And there is a second line of defense that are structural interventions, like, for example, in this picture from Japan. But in some cases, urban planning is no more an option because maybe we find that we have already made, we inherit a bad urban planning from the past. And in some cases, structural interventions are not doable, or like in this case, they maybe are doable, but not always so acceptable because of environmental impacts, or also because of high costs, or sometimes because the landslide is so huge that it is not possible to make any structural interventions to reduce the risks. So in these cases, we can resort to early warning systems. We have seen some definitions of early warning systems and early warning and monitoring. I will present you a definition that comes from different authors. I've made like a remix of the definition coming from different authors and from the definition of the United Nations. And so this mix brings us to seeing early warning systems as a sum of 4 different components, which are the design, monitoring, forecasting, and education. And usually it is quite common to confuse early warning with monitoring. We have already seen some differences, but we can think of monitoring as a part of early warning systems. So if we want to make an early warning system, we have to think that monitoring is not the only thing that we need. We also need some other parts that are that involve scientific and technical aspects, but not only. We also need to implement organizational, social, planning activities. So, for example, we can think about these 4 components as different phases. We don't have exactly a temporal succession between these different components, but somehow we can think about with some approximation, we can think about this as a temporal succession. So first we have the design phase where we are planning on how we want to make our early warning, and we have to first of all study the problem. We are talking about landslide here, so we are making probably modeling and risk scenarios, geological surveys, geotechnical surveys. The same goes also for other types of threats. So early warning system can be used also against pandemics, for example, or against any other risk. So this structure is more or less the same. We always must have a design phase at the beginning, and we also have to define what will be the best indicators that we want to monitor. In our cases, I will talk about indicators such as displacement, but in some other cases, rainfall can be an indicator of failure, but then can be others as well. We also have to define what are our priorities. This might seem something obvious, but it is not so obvious, because in some cases, false alarms can be more acceptable than in other cases. This depends on the culture, on the type of risk, on the presence, for example, of structural interventions. So we have to define how we want to reduce this risk and what is the threshold of acceptable risk. So this is something that will influence the rest of the early warning system, and is something that usually is to be done beforehand. Then there is the monitoring part. I will skip this part. We have already seen earlier some instruments that can be used on monitoring, but this can be thought as the core of the early warning system. Then there is the forecasting part. I will focus on this part in my presentation. And finally, the education part, which is by far the most cost-effective means of reducing the risk, because the education of the population to, for example, learn safe behaviors. So how do you behave in case of a certain risk? In case of landslides, for example, you have to learn that the most dangerous times to be outside in the mountains would be maybe during heavy rainfall, or against flood. You have to know that you don't have to pass by bridges, for example, if possible. And so it's the topic of this is to have a relation with people, to the people exposed to a risk, to involve them as much as possible. In fact, this part is so important that many early warning systems are called people-centered. So we have really to focus on people, and because the aim of every early warning system basically is to save people, because you want to have the elements at risk, that in this case are people, put outside of the reach of the threat. So the early warning system will usually not be able to do anything against structures, because generally they are not movable. So they only can intervene for people and also animals. So this fourth component really is the most cost-effective, but also the most neglected part of every warning system usually. But what I want to stress here is that although I will focus about this forecasting component, but any of these four components is fundamental. So a lack in any of these will probably mean the failure of the whole system. Which is something that is symbolized by this slide. We can think that the aim of the early warning system is to provide an alert, but since the alert is only the final aim, but this is like a chain, and every ring of the chain is a different component, different activity, and if one of these rings breaks, then the whole chain will break. So we really have to focus not just on, for example, monitoring or, for example, forecasting. We have to have an overall view of the early warning system. So as I said, I will focus on forecasting methods. First of all, what I will not talk about, I will not talk about forecasting methods based on rainfall. We have already seen very nice presentations about this. I will not talk about forecasting methods based on there are many methods that are not based on displacement, not even on rainfall, but they are based on a variety of parameters and a variety of precursors. And for example, this is a work from Sveditsky from 2003, where he collected a series of geological indicators and precursors that can forebode some possible failures in underground mining. So for example, if you see spalling, or if you see, for example, convergence of the walls, and these are all signals of possible failure, and some of these signals can be also measured. For example, the acoustic emissions due to cracking of rocks that are breaking, or the rockfall frequency that is increasing before a larger collapse, or the pore water pressure. There are some methods that are sometimes used, but this is a very interesting field, or many fields, but these are not very much structured. The most structured way to make slope scale forecasting is the one based on displacement measurement, or as I wrote here, kinematic parameters, because we don't have just displacement, it can also have velocity or acceleration, so the derivative of displacement. We can broadly group these methods into two methods, like empirical methods, semi-empirical methods, and also we can think of another couple of methods that are not properly forecasting methods, because when I say forecasting, I mean that we have to define the time of failure of a landslide, but there are other methods that are usually very often called forecasting, but they do not provide a time of failure. They just provide a warning. So, for example, methods based on thresholds, they can provide some warning, but they cannot provide an actual time of failure. So first of all, the empirical methods. All the empirical methods are based on the creep theory. Creep is a behavior of material, also not just landslides, not just soil and rocks that make up landslide, but also other materials. But we are interested in landslides, so is a behavior that it is not always present, but usually can be seen, especially before the failure of a rock or a soil. And this behavior is characterized by three stages. A primary stage that usually displays deceleration, a secondary stage that usually displays linear velocity, and finally a third stage that displays an acceleration, an exponential acceleration. The first stage is not always easily recognized. The secondary stage represent linear velocity, as I said. So this means that we have no acceleration. And so if we have no acceleration, this means by the Newton's law that we have an equilibrium between forces acting on the landslide. So if the forces are at an equilibrium, this means that the destabilizing and the stabilizing forces are also in equilibrium, which is the definition of the factor of safety. So a linear velocity usually means that we have a factor of safety close to 1. We have maybe a slow movement, but this movement is somehow considered not too dangerous, but probably we may want to already have installed some monitoring instrumentation because the landslide is not stable, is at an equilibrium limit. And from this part, we can have two possible outcomes. So if we represent the same graph using velocity instead of displacement, this means that the linear displacement will become an horizontal line, and then we can have two possible outcomes. We can have maybe we have an acceleration, but then this acceleration can stop, maybe because we have had a rainfall event, so the landslide had a very small acceleration, but then this acceleration lasts for maybe a few hours or a few days. And then the landslide reaches a new limit equilibrium, and this equilibrium can last for an undetermined time period, for example, for one season, maybe until the next rainy season, or maybe even more. Or actually, this is the secondary creep is a stage that nobody really knows how to make forecasting from this stage, because the duration of this stage is almost impossible to determine. On the other hand, a second possible outcome is that this landslide continues its acceleration. The acceleration is exponential, so the velocity increases also of maybe of an order of magnitude. And so usually when we implement threshold, we are very conservative, but actually before failure, the velocities really increase of 10 times or something like that, even more. It depends, of course, on the landslide. And this trend here usually is can be so regular that we can try to make some extrapolation and provide a forecasting of the time of failure. Also, note that when the velocity of movement of the landslide is very high, this also means, importantly, that the signal to noise ratio tends to increase, because the velocity measured is so high that the small noises that usually affect the background noise that affect an instrumentation are usually much smaller than the actual displacement. So this is easier. This make prediction a little bit easier. The first, well, this is not the first method, but this is by far the most common method used to make predictions, has been developed by Fukuzono in 1985. This is an image taken directly from that paper. And he had an insight, a very simple idea. And he realized that if the velocity is increasing exponentially towards infinite, theoretically, and until it reaches, the velocity reaches, well, it never reached at this asymptote that corresponds to the time of failure. So he argued that if we display the inverse number of velocity, then the inverse number will not tend towards infinite, but of course it will tend towards zero. It will never reach zero because the zero would mean infinite velocity, but we can trace the inverse velocity against time, and then we can extrapolate when theoretically this line would touch the time axis corresponding to infinite velocity, and this time would represent the failure. So it would represent this red line here. The point is that usually when we implement this method for our landslide, we always consider that this inverse velocity assumes a linear shape like this. This is not always the case. Actually, it is more probable that the trend is not exactly linear. It can be either convex or concave. In these cases, when it is convex or concave, the application of this method is not just a simple extrapolation, but we have a little bit more complex geometrical method it is an empirical geometrical method to obtain the time of failure. I will not go into detail of explaining this method, but basically we just need to reproduce some geometrical features on a graph like this, and we can obtain a red line like this that will give us the time of failure. There is also an analytical way to solve this problem when the inverse velocity is not linear, and the analytical is provided by Fukuzono himself. This symbol here is a Greek letter called lambda that is used sometimes by some author to represent the inverse velocity because it looks like a v of velocity but upside down. So it's a very simple equation, and if we provide these values, so that the time taken into two different points and the inverse velocity corresponding to these two different arbitrary times, we can obtain the time of failure. This method is actually quite powerful because it can provide time of failures not just of landslide, but also of concerning other kinds of failures. For example, it has been used to forecast the failure of the Volterra medieval city wall. Volterra is an ancient city in Florence. Actually, it is even older than medieval times, but it is also famous for this medieval city wall that a few years ago were affected by two different collapses. So after the first collapse, we were summoned to install a ground-based interferometric radar. This radar had this field of view covering a large section of the city walls. And while we were making the monitoring, we realized that a part of this city wall was starting to display a behavior like this. So it displays, this is a velocity. So an increase in velocity. Afterwards, we tried to implement the Fukuzono method to see if some trend would come out from this velocity time series. And we realized that if we use raw data, the time series was a little bit too noisy because the velocity here was not so high to increase the signal to noise ratio, as I said before, but we just needed to implement some filtering to obtain a very nice time to failure. These results are published on a paper that you can see that the reference to the papers, and you will see references to papers all over my presentation if you want to have other details about these case histories that I will present. Outside from empirical methods, there are also some methods that we can call semi-empirical. The most famous semi-empirical method is the one developed by Barry Voigt, who generalized the method of Fukuzono. The method of Barry Voigt, I call it semi-empirical because there is still a part of empirism, but he tried to put some physics in it so that this method was not only like a black box. And he developed this method and applied it to volcanic eruptions, which is very interesting because once more it establishes that this creep theory can be applied not just to landslide or to city walls, as we have seen, but in general it is a behavior that is more intrinsic to collapses. It seems that many different materials and also environments can respond to this model, this creep model. So the method is can be represented like this, where we have this letter omega. This is the second derivative of omega, and this is with one dot the first derivative of omega. And what is omega? Omega is intended by Voigt as any parameter that can be seen as useful for our representation, for our forecasting. As I said earlier, we have to define what are the geo-indicators. In the design phase, I said we have to define what are the geo-indicators that we want to use to monitor. And I said that we have displacement, but we also have other indicators, like, for example, acoustic emissions, rockfall frequency, and so on. If you think about a volcanic environment, you have even more indicators because you can have all sorts of seismic indicators, geochemical indicators. So you just choose one. You need an indicator that you will know it will increase before the collapse. And for example, in our case, we can think that omega is displacement. So this here is the velocity, and this here is the acceleration. And so he found out that velocity and acceleration are related by this linear relation if you use a bilogarithmic diagram. The angular coefficient and the intercept of these two lines are represented by A and alpha. A and alpha are very variable, especially A. It can vary from like 5 orders of magnitude. So it is not possible to provide some literature values of these two parameters that maybe can be used for our particular case. The best thing is that we collect some monitoring data, we measure some velocity and acceleration values, we plot them, and we obtain the interpolation, or by interpolation we obtain A and alpha values. We put A and alpha into this equation and we obtain the time of failure. My approach to early warning and forecasting is follows the prediction theorem of Page. Scott Page is not a geologist. He is an expert in social sciences, but in 2007 he demonstrated mathematically that if you put inside the room a team of decision makers and you ask them to make a prediction, their prediction will be more accurate if these people are as different as possible. So, for example, if they have different ages, different sex, different cultures, and different experiences, and so on. So I believe that the same can be applied also to forecasting using any prediction model. So if you put together, for example, the Voigt method, the Fukuzono method, and also there are many others that I have not shown here for time reason. But if you collect all these methods together, you apply all of them, then in the end you can obtain a prediction that is more accurate than what you will obtain using just a single method. So if we can use a metaphor, it's like as if you want to get to your solution, which is an accurate prediction. So this is your target, and to arrive here you can use like you can arrive here through a highway, which is represented by a very robust method, maybe the Fukuzono method, which is the most used. But sometimes Fukuzono method just cannot work. So you have an obstacle because, for example, you have a noisy time series, and which is quite possible because if the velocity is not too high, it is easy to have a noisy time series with Fukuzono because you use a velocity, so it is a derivative of displacement. So the velocity is more scattered than displacement time series, and also you make the inverse velocity, which also increases even more the noise. There are other methods that can be used that maybe have other limitation, but not this one. And so singularly, they may be less accurate, so which is represented by smaller streets. So this maybe if you take them singularly, they cannot be as reliable as these other models, more popular models. But if you use all of them and you see that many of them go towards the same predicted time of failure, then this will give you, of course, a higher reliability and confidence of your prediction. So mathematically, it's something like this. The red dots represent a high precision but low accuracy because you forecast something that has an average on this red line, while the true value would be the green line. So if you implement other methods that maybe are less precise, like these blue dots, maybe they are less precise, but on average they are they will give you results that are more accurate. And this is not just common sense. This has been mathematically demonstrated by Page. So, for example, we can make a prediction using a plot like this. We can use prediction using, we can make prediction using, for example, 3 different methods, here represented by the letter of the author, of the inventor of the method. So the F letter is Fukuzono method. M is another method represented that was developed by Mufundirwa, and this here is a method developed by Saito, but I have not talked about these 2 methods, but just as an example, we can have any forecasting method. In this plot here, I represent the time of the prediction. So when is has been done the prediction, and here is the predicted time of failure. So, for example, we can say from this graph that at the end of October, we have made a prediction of this lens that it would have collapsed at towards the end of January of the later year. Here we are at the beginning of November. At the beginning of November, the prediction changed, and it predicted a failure about the beginning of December, for example, and so on. You see that every method gives different predictions. So, for example, this method here, it never converges towards a certain prediction, while these 2 other methods, you see that they kind of oscillate around an average time of failure, which is represented by this red dashed line here. And this red dashed line here actually happens to be the real time of failure of this landslide. This is a landslide that collapsed in Monte Beni, which is a place in Tuscany in Italy. And which have been correctly forecasted, not using only for Fukuzono method, but here I wanted to demonstrate that if you continue making your prediction through time and study how the prediction changes through time and compare it also with other prediction, you can achieve a higher accuracy. I also note that the latest predictions, like for example, this one, and this one, and this one, are not necessarily the most accurate. So, for example, this very early prediction occurred to be a quite accurate prediction. So you have to see the whole, if possible, you have to see the whole process of prediction, because it is not necessarily true that the most recent predictions are also the most accurate, which is usually considered like this is the case. Of course, it is necessary to update your prediction to the latest evolution of the Landslides, but we also must not disregard the past behavior of the Landslide. So this was as far as empirical and semi-empirical prediction are concerned. I will say just a few words about other methods that are here I call numerical methods. Numerical methods are very popular, especially in the Chinese community, and they rely on different techniques, artificial intelligence, for example, or statistical methods, like in this slide here. Usually, what they do is that they have a time series that they want to predict the values of this time series, and there are different ways to make this prediction. For example, one way is one way is to model the time series as a sum of a cyclicity, a trend, and a seasonality. There are also other methods that I will skip, but in general, the idea is that we have a trend line like this, and we want to make a prediction, like, for example, the one provided here by the red line, and then possibly we also want to provide a confidence range, like the one here provided by the green line. And in many papers, this is called a prediction, a Landslides prediction, but I do not agree with this definition, because this is a prediction not of the collapse of the landslide. This is a prediction of the velocity that the landslide will likely have in the future. But this information alone is not necessarily useful to make warning, because if you tell me that tomorrow the velocity will of the landslide will be, I don't know, 1 millimeter per hour, but this does not answer the question if should I worry if this is the velocity, or can I say my citizens that they can be safe and sound. So I think that the only way that these methods can become useful for early warning is that we provide a definition of thresholds using this method. So the definition of threshold can be used, can be developed, for example, if we implement this confidence range. So we can say that we have a confidence of the 90% that the velocity tomorrow will be within this green band, so between these two green lines. If the velocity is higher than this green line, then we have a problem. We have something that we have not forecasted. We have an anomaly. So there is only the 10% of probability that the velocity was so high, and so we have to probably to set a warning, or maybe a pre-warning or something like that. But usually this final step is rarely seen in paper, and so this is why I would not call them exactly forecasting methods. About just 7 minutes, okay, I will just cover one last topic that concerns failure predictability. This is a huge topic in prediction. The topic is okay. We know how to predict landslides, but we have seen that for some reasons we are not always able to make predictions of landslides. It's not that every landslide can be predicted, and so the question is why? Why can we predict some landslide and why not? So what are the characteristics that make a landslide predictable? I want to quote some authors. These are two very famous researchers, Aldrich Hang, who passed away a few years ago, and David Petley. These are prominent landslide researchers. And Hang, together with Rose, made a paper in 2007 that somehow resurrected the Fukuzono method, because Fukuzono method was from 1985, and before him, Saito in 1969 invented the forecasting methods, but then they were not very much used, and they were rediscovered by Rosenhanger in 2007 somehow. Petley, he always had an interest in Fukuzono and Saito, and they made some papers that I quote here that give somehow apparently contrasting assessments. But the value of these two researchers is there is no doubt about the value. So it is not that they are wrong, but there are some things, some tricky things that we need to understand. So, for example, Rosenhanger in 2007 wrote that only ductile landslides with a ductile behavior are expected to be linear, and that brittle rock is not forecastable. So they say basically that if we want to make a forecasting using Saito or Fukuzono, we need like soft rocks or soil, but not brittle rock. On the other hand, Petri said just the opposite. Says that the linearity, so the fact that the inverse time of failure is a straight line, so the extrapolation towards the time axis is very easy, so prediction can be made very easily. This is a behavior typical of brittle deformation, and he reconducted the brittle deformation to first-time rupture, while ductile deformation is typical of reactivation, and usually it is very difficult to make prediction on these cases. Probably the truth is a bit something in between, so we cannot be so tranchant about this matter. Probably the truth is a bit more blended. For example, I have a very famous landslide in Italy, that is the Vaillant landslide, that it is a reactivated landslide, but displayed a very brittle behavior like this, with a very spectacular linear inverse velocity that was quite easily predictable. You see the red line here is the time of failure, and the predictions are more or less centered on this time of failure. Of course, at the time, we did not have the knowledge about this, about these methods. There are other cases. For example, this is a failure from the United States, from a quarry. In this quarry, explosions were used, and these explosions triggered a landslide. So you can see here the acceleration due to 3 different explosions. And although this is expected to be a first-time failure in quartz monzonite that should be expected to be quite brittle rocks, but despite David Petley said that first-time brittle failure should display a linear behavior. In this case, we don't see a linear behavior. We see something like this, a concave inverse velocity that is still somehow predictable, although the prediction is more difficult and it is easier to make errors. But so this is another exception to what we have already seen. We have also seen other similar cases for Stromboli volcano. You see here the velocity and the inverse velocity, which is not linear. You clearly have a concave trend. Also, in this case, we have a brittle first-time failure, but we also have external forces where there are not explosions. In this case, there is magma pressure, but this complicates the system. So one may argue that Rose and Hang were right, but this is not even the case, because we also can make prediction on very brittle rock. This is, for example, a case from an open pit mine in metamorphic rocks. And in this open pit mine, if we study the displacement of these mines, we see that, and the velocity, we see that the velocity is more or less stable until the very last, where we have very strong acceleration. These are 4 different failures, but in all cases, you see that the acceleration is very abrupt. So this would seem something impossible to forecast, but it is actually not a theoretical limit. It is a practical limit, because even if the acceleration is so abrupt, we always have, or almost always have, a tertiary creep, so an acceleration that can be modeled using, for example, Fukuzono method. So except for the first case, where we don't have a linearity, for the 3 other cases, we do have a linearity with just few hours of advance, but that can enable, for example, the operators of this mine to take cover. So, for example, and so it seems that actually it is a matter of how our instrumentation are able to make real-time monitoring. So to conclude, I'm approaching my conclusion. The point is that it's not that from the geology it is directly possible to say if a landslide is predictable. It is not. There is not this kind of relation. Probably we must think of something a bit more complicated, because from the geology we can determine the kinematics of the landslide, so the shape of the displacement curve, and from this shape we can define if this landslide can be predicted or not. But the passage from the geology to the kinematics is the real problem, because we have a lot of different things and factors that come into play. For example, structural constraint, rainfall, external forces, as we have seen. So it is not possible to determine, by knowing the geological context of a landslide, what will be the shape of the displacement curve, and which is also the main problem of predictability. The good part is that this also means that we are theoretically able to make predictions also in much more cases than we used to think. For example, earlier researchers warned that prediction was not possible against brittle rocks or against reactivated rocks or landslides, or for example, against landslides that experience external forces and so on. This appears not to be the case, or at least not always the case. And in fact, these methods are quite powerful and can be used in a variety of environments. Finally, let me make a bit of a commercial about the World Landslides Forum. Veronica Tofani and Samuel Segoni already did it yesterday. Let me join them. There will be a session about this topic and in the World Landslides forum. So if some of you is interested, you are invited to take part to this this session, or in general to the forum. Thank you.
Thank you, Emanuele, for your nice presentation. Do we have some comments or some questions from the audience? In the meantime, I would like to stress that Emanuele provided us with a brief overview due to time constraints about the topic of slope scale monitoring and early warning, but he has a full course at our PhD school. Correct me, Emanuele, if I'm wrong. And so for the PhD students who are interested in more details, they can contact Emanuele Intrieri and for signing into his full course about these topics for the PhD school. So,
thank you for mentioning it.
Yeah.
So I'm sorry if other PhD students that are here already heard me telling some of this stuff, because maybe there are some that follow my course in the last year, but they already heard it. But that's it. The audience is quite different for the rest. So I thought that it would have been okay to say something like this.
Yeah. You provided us some pills, and then if somebody wants a larger portion, can join your course, of course. Yeah, okay.
Hello.
Yeah, please go ahead.
Hello. Thank you very much. And about that course, is it offered online?
Oh, the course is yes, it is a PhD course. So the aim is PhD students, but I think that if you are interested, we can arrange. I don't know your position, but I think sure we can arrange things. And if you're interested, you can contact me. You have my email address I can share it, my email address. If you're interested, you can
write
contact
it in
me.
the chat.
Okay,
and
I can keep you updated about the time of the course when it will be activated. It will be in early summer or late spring.
Okay, thank you very much.
Are you planning to do it on remote, hybrid mode, or on presence?
My idea is full remote.
Okay.
Because there will be students from other cities already.
Yeah. Maybe this is an important details for those who are maybe interested. So maybe also from India, they can join if they want.
Yeah.
Yeah, you can share the details so that, I'll send it to all the participants.
Okay,
sure.
Cool. Do we have other questions or comments about this presentation given by Emanuele? If not, I thank you again, Emanuele, for your talk.
Thanks to you.
And I will move to the next speaker, which is Dr. Tadikonda Venkata Bharat. Again, I apologize for any mispronunciation. He's currently a professor of geotechnical engineering in the Department of Civil Engineering, and he's an associated faculty in the Center of Disaster Management and Research at Indian Institute of Technology, Guwahati. He worked as a visiting fellow and postdoctoral fellow during the years 2009-2012 at the University of Saskatchewan, Canada. And he has his research interests are the mitigation of rainfall-induced landslides, waste management, and geotechnical and architectural aspects of heritage structures. Dr. Bharat has published over 60 peer-reviewed articles, book chapters, and conference papers. He has received numerous awards in India and abroad for his contribution to computational geomechanics and geoenvironmental research. He's the editorial board member of the Indian Geotechnical Journal, and he is an active reviewer for over 25 peer-reviewed journals. He is also currently one of the expert advisory committee members of the Waste Management Technologies Program of Technology Development and Transfer Division of the Department of Science and Technology at the Ministry of Science and Technology in India. So, Dr. Bharat, are you okay? Yes, I see you here. Good afternoon. You can go, you can share your screen if you want.
Yeah.
Just a few seconds. Okay. We see the screen.
Are you able to see the screen?
We see the screen, but it's not in the presentation mode yet. Yes, now it is.
It is turned on.
Yeah, everything is in order. So please, you can go ahead.
Thank you, Samuel. First of all, I'm very thankful to the organizers, especially my good friend from IIT Indore, Professor Nilima Satyam, for inviting me for this particular workshop on landslides. And first of all, I apologize if there is any noise because I'm traveling. I'm not in my hometown. I'm on some duty, and if there is any noise or any technical hitch, please let us know. Let me know. I'll reconnect through phone or something. And as of now, I think there is no problem. And let me start the presentation. So the title of the presentation, that is, envisaged as Occurrences, Mechanisms, Prediction of Rainfall-Induced Landslides in Eastern Himalayas. I'm from IIT Guwahati. Guwahati is located in the northeastern part of India. Yeah. So in India, we are the northeastern part, where in the northeast India we have 7 states. Of course, including the Sikkim, there are 8 different states or different provinces. Where the Assam, where the IIT Guwahati is located, and Arunachal Pradesh, Nagaland, Manipur, Mizoram, Tripura, Meghalaya, and Sikkim. These are other different states where cultures, everything is quite different in all these states. So interestingly, first of all, the northeast state of India is highly scenic, very beautiful, with mountains, valleys, and rivers. And it connects to several countries like Bhutan, Tibet, China, Myanmar, and Bangladesh. So it shares international borders with all these countries. And the time frame, if you see in the summers, the sun rises at 4 o'clock in the morning. And sun sets early also, especially in the winter, sun sets by 4. So there's a huge time lap between west coast and east coast, eastern part of our country. And the monsoon starts very early. By March itself, the monsoon starts. And a few showers it shows. And after that, this is the longest monsoon or longest rainfall that takes place in this part of India, where from March to nearly October, the monsoon takes place. So most of the landslides are, expected in the months of June, July. The floods take place in the months of May, and landslides in the months of June, July, again in the months of September, October. So in the northeastern part of India. I'll anyways discuss about these things after a little while. So this region receives the highest rainfall. In fact, some of the regions are wettest part in the whole world. And these are younger mountains compared to other places. And this often frequent earthquakes occur in these regions. Coming to the rainfall, so over 2,500 mm rainfall takes place in this region annually, and average annual rainfall. And some of these places like Mysindra, or earlier it was Cherpunji, was the wettest place on earth. And the received rainfall is this much, very huge rainfall. And due to the climate change, often what we see is that the rainfall patterns are also changing, and the average rainfall is also significantly changing. With coming years, we are expecting that more and more rainfall amount will increase because of the climatic changes. So coming to the topography, so as I said just a while ago, there are mountains and even valleys in some part. So many rivers are flowing, and in fact, interesting geology. And if you talk about the rivers, we have a major river, Brahmaputra, which originates in currently China, Sangpo. The Brahmaputra is called Sangpo in China, and which travels towards east and enters to India, and which again travels towards south and merges with the Ganga, and then it becomes Padma in Bangladesh and enters into the Bay of Bengal. And also there are several channels originate from different parts of the northeast India and then merge into Brahmaputra. So this is also a terrain map which shows the geology of the whole region. The geology, the river basins, and these things are very, very important when we are talking about landslides. And coming to the seismicity, this falls under zone 5, and so the region consists of several banded rocks, several fault zones, and seismically very active, this particular place. Coming to the geology, it has an interesting rock mass. Gneisses at one place and shales in many places like Manipur, even in Assam. Of course, the weathering class would change for the shales, and conglomerates, sandstone, limestone in especially Meghalaya, and also you have coal in Meghalaya. So a lot of mining takes place. So you have schist, and especially in the Arunachal Pradesh region, and megmatite, marble, and other things. So you have interesting geology, a lot of variations. Coming to the recent developments, the anthropogenic activities that are taking place, mostly because the development activity that is taking place. As I mentioned, the international boundaries are very close by from the place where I reside, Guwahati. So there are a lot of development activities that are taking place because you all know that there are some aggressions are taking place with other neighboring countries. So there are developments by Indian Army, border roads, and so NHA, DCL, and NFR. A lot of pressure has been given for the development of roads. The 4-lane roads and other things are currently developed in this particular terrain. So there are few hydroelectric projects are also going on, especially in Arunachal Pradesh, where about 40 to 50 megawatt power hydroelectric project is actually currently running, where there is one landslide which I will discuss very soon. So this is the landslide susceptibility map, and which shows that the northeastern part definitely receives a lot of landslides, and of course other parts also. If you see the global map, the northeastern part actually is under hotspot area, where a lot of landslides they receive. And this became almost common that every monsoon in the months of June, July, obviously we receive certain landslides in all around. So landslides we just define simply as the movement of mass of rock, earth, or debris down a slope. So there are several factors that influence anthropogenic, earthquake, rainfall, volcanoes. If you keep the volcanoes aside, because that is not active here, the other factors like anthropogenic, earthquake, and rainfall, these are all interlinked. So when the development activities are taking place in this particular region, so there are cutting of the toes and a lot of intervention of the human beings are taking place. Also, there are mining activities. As I mentioned, coal, limestone, all these things are available in some parts in Arunachal Pradesh and mostly in Meghalaya. So when the mining is taking place, which actually disturbs the whole mass. So which is done not much with engineering intervention. So especially the earthquake also influences. Earthquake might not trigger, because I have not seen in northeastern India that earthquake will not trigger landslide immediately, but earthquake definitely influences the landslide, has influence of the landslide in this part of the country. So rainfall, major triggering point. During the rainfall events only, they are happening. So these are some of the recent landslides in northeastern India. I will briefly mention some of them and then I'll emphasize few landslides in coming slides. So this is one landslide which is in Jaiguru, Assam, which is adjacent to our campus, IIT Guwahati campus. So the failure, if you see, a large rock mass has actually come down. Even one of the rock piece, which is about 50-60 feet wide, that has actually rolled down from the hill and then which occupied this 4-lane road. So during the year 2020, probably the June, where the lockdown has just started in India. And subsequently, within 2 days, there is another huge landslide that has taken place. Here, it's kind of a mud flow. Mostly the laterite soil has actually came out and then it started flowing. This is called Raj Bhavan, where the governor's bungalow is located on the hilltop. And this hill, there are repeated landslides that are happening, and one of the major landslides that occurred during that particular year, 2020. And this is in Tippi, Arunachal Pradesh. We were actually traveling to forward areas in the months of December. And so in majorly around a stretch of about 20-30 kilometers. So severe landslides, and the geology varies drastically from one place to another place. Multiple landslides in different regions. And this Shillong bypass, Meghalaya, this is recurring, every now and then. And here some benching or something has been provided. And I'm not giving more details on the solutions that have been adopted, because my major concern here is the prediction or the mechanisms of the landslides. So I'll speak about the measures that in some other time. So this is in Arunachal Pradesh, Likabali, and this is very interesting thing, which is currently the landslide is still active, even though this is not monsoon. Still, this is active. I'll discuss in a while. This is again, I'll discuss very detailed about this landslide, and these landslides anyways we'll discuss. So the Offlong, this is in the lower Assam, this is northeast, and this is Assam. This is a part where Offlong. Offlong is a place in Assam where the railway station is located at the foothills of 2 hills. On right hand side you are seeing one hill, and on the left hand side also there is another hill. So this is a very scenic, beautiful place. In the May 2022, just last year, not even 1 year passed, there was a huge heavy rainfall for several days, and whole debris has come down. If you see that particular hill on the left hand side in this picture, this looks like this. So this is the highway, which is actually connecting the Offlong city from the foothills, and the landslide has triggered from this particular point, which is about 150 meters from the 150 meters above the railway station. So this is the initiation point. It actually triggered. So this is the initiation point where the landslide has started. and it came down, and then whole debris has actually settled here, and it pushed the train bogies and other things. This whole area got disconnected for several days. This is like a flood-like situation that has happened during that particular month, and many people have got stranded and in this railway station. And from the hill, this is the railway station. This is about the recent landslide that has occurred in Aflong. And these are the optical images, satellite data that was provided by Northeast Space Application Center, ISRO, ISRO, and the damages can be easily monitored using the Cartosat data before and after the landslide. This is the landslide, which I said, very interesting landslide, very interesting case study, where is just a border to the Assam. This is in Arunachal Pradesh. The Dhemaji district is very close to this particular place. Along this Likabali hollow region, this particular hill started moving towards the Siang River. This is the river. So the Siang River is actually flowing this side. Wherever there's a bend, Siang River, which actually takes a bend and then moves like this. And at that particular point, this particular hill started moving towards the valley side. And this started blocking this way. And now, this particular road section got narrowed down. Earlier, it was a 2-lane road. Now, almost more than a lane was completely gone. And this is still active. This is still moving. Here, there is a bridge also, because here there is a water flow that takes place, and drainage has been provided under a bridge. And this bridge deck started uplifting because this hill is actually hitting the bridge deck, and this bridge deck, so bridge is actually started upheaving. So there are visible cracks on the ground on the road section, and the geology is very, very weak. Here, mostly the sandstone and few shales are also available. So this is a Mao region in Manipur. I don't know whether exactly this can be called as landslide or ground settlement subsidence. So on the valley side, this is the valley side, and this is the hillside. So about a 35-kilometer stretch, the whole landmass is actually getting down or going towards the valley. So all around it. But on the hillside, this is kind of a stable. So earlier geological report mentioned that the whole hill is moving, but visually it doesn't show any movement by the hill. But visually what appears is that there is a huge settlement of the ground or road. Even at certain locations, there's a 3-feet settlement of the road towards the valley side. So again, this is a 2-lane road, and this is a very important connection to Manipur and Nagaland from the Assam and mainland. So currently this has hit, and this is a very pathetic condition currently. This is one of the landslides in Sikkim, and I think there was Mr. Deepak has presented from Terami some time back before me about one landslide restoration or slope stabilization using reinforced earth wall. And here this is a Rangpo site where similar measure was about to take place using geogrid and other things, but it failed during the execution in the month of February last year. So this is a CCTV footage where the landslide has taken place. Interestingly, this is not induced by rainfall or any other thing. During the execution, because this is the Tista River, from the riverside, the boulders have been taken and then they are used for the backfill, which are rounded in shape, which has almost like a no friction or very less friction and then the heavy weight. So I think this is one of the major reasons, and also anchoring was not good, and there was no detailed analysis that was done, and then the whole thing has actually collapsed. So this is one of the interesting case studies. This is in Meghalaya, Shillong. I'm almost touching all the places in Northeast India, which were recently happened. So this is in the Nehu, Northeast Hill University, Shillong, where you have athletic ground, and on the valley side, there was a major landslide that has occurred, and the height of the slope is about 60-65 meters. Here, this is the breast wall. Breast wall also collapsed partly, along with the sliding mass. And this collapse has occurred and on particular day, so June 27th, 2019. And after that also there were few triggering things, and a few mass has actually gone down. And immediately we suggested some measures, and after that this got restored. So let us see what prediction methods are currently available on landslides. So after understanding some of the landslide events that have taken place in this region. So currently some of the statistical models they based on the rainfall thresholds, based on the rainfall intensity, rainfall duration. So even now, the NESAC, that is a Northeast Space Application Center of ISRO, uses some of the statistical models for prediction of the landslides in this region. And little more advanced, where NASA also uses currently, are based on antecedent rainfall index. So if you see the same region in the month of March, these are all the susceptible areas, because more amount of rainfall might have might have occurred in these regions. So based on the antecedent rainfall index, they are classified under high risky regions. But in the month of August, they are not. But that means they dynamically change these regions for the susceptibility things. But however, we should not forget that all these models have major limitations, because they heavily depend on the rainfall data, and the reliability of the rainfall data is highly unknown, unpredictable, because first of all, they don't consider the geology. For the same geology, even though the soil conditions, weathering classes might be different, and the availability of the groundwater table is also might be different. Because of that, the poor water pressure and negative pressure in the soil mass could be different. And also the flow behavior could be different, and slope angles could be different, surface runoff could be different. And therefore, so these existing statistical models do not consider any of these parameters in their consideration for predicting the landslides. So also, in fact, the initial soil moisture also plays a very important factor, because as I mentioned, so as during the March or April, the rainfall starts here, and early in the months of May, when the intense rainfall start, first of all, flooding takes place, because the soil will have very low hydraulic conductivity. The flowability or the infiltration rates are low. So therefore, the flooding takes place. So in the months of June, July, where some water actually got into, and now the rainfall, the hydraulic conductivity increases slightly bit. So therefore, the failures takes place in the months of June, July. So therefore, physics-based models are better and more promising for predicting the landslides. So the mechanisms could be well defined why the landslide is actually happening. If you look at, if you have a truck of sand, dry sand, if you just unload it, it occupies a certain angle. There is an angle of repose, which is angle of internal friction of the soil, if the soil is completely dry. But using sand, it is possible to make a vertical, objects, something like this. This is possible because which soil is partly saturated. Because when soil is partly saturated, like something like this, so when the soil is partly saturated, something like this, which has surface tension force. So this tensile or additional shear strength coming from the surface tension force binds the particles together. So therefore, even the vertical cuts are possible using the sand, right? So that's how we make castles on the beach using beach sand. However, beach sand, just if you take a dry sand and then pour it, it hardly takes about 30-40 degrees. That's all. right? So similarly, in the soil, it can have a steeper slopes. So during the construction activity, we may cut the toe, and then still, even if you have a 90 degrees cut, nothing happens during that particular time. But then slowly, as water percolates into the ground, and the shear strength will be lost because of the saturation. So this is a negative pore water pressure. The pore water pressure is negative. That eventually becomes positive, and also the shear strength, the additional shear strength component is actually got reduced, and because of that, this failure takes place. So what exactly is happening during the development process? I'll just explain. So before the development or any other road construction, this is the scenario where you have a nice slope, and then this is the valley side. You have some river which is flowing, and you may have a saturated soil. This is the groundwater table, and then when rainfall takes place, so mostly the surface runoff takes place, which is very shallow. At a shallow level, our surface runoff and subsoil runoff takes place, and which enters into the surface water. There is nothing but river or something. But when we construct a road here, when you cut here, so eventually what we'll do, we'll actually make one protection here, retaining wall or something. Here we construct a breast wall, and then we make a road, and then have our normal activity. So when rainfall takes place, the water which is actually coming down from the hillside will try to enter here, because if proper drainage is not provided, so eventually the pore pressures increase here, which can push the, pore pressures will actually accumulate over a period of time, and then whole mass will actually try to push this, and retaining wall will fail, and then whole mass will start moving towards the right. Or sometimes, if it finds a better pathway, it tries to flow underneath the road. If the soil is such that it is a collapsible soil, because I forgot to tell you that in this part you have plenty of deposits of kaolin, China clay it's called, because possibly because close proximity to China, we have a lot of deposits of kaolin, white clay. So kaolin actually collapses during the wetting. During the dry time, when the soil is dry, it can take a huge amount of load. But when it is actually getting wet, collapses. Volumetric collapse takes place immediately. So we have such scenarios in some parts in Assam, where about 35-kilometer road has completely got subsided. And so that could happen. It would actually trigger, and then it will push the breast wall here, because eventually it wants to travel towards the valley side. Proper drainage, surface draining, and the draining proper networking would have actually saved this whole thing. But eventually, during some of the reasons, when the proper engineering intervention is not made, these kind of failures would trigger. And I was saying, above this groundwater table, the soil will be negatively, the soil will have negative pressure, because simple analogy in soil physics, what we learned, if you insert a capillary, there's a water raise that takes place, a capillary raise that takes place. To what height? This is a capillary height. This depends on the radius of the capillary. So as the radius of the capillary decreases, the height of capillary raise increases. So eventually in this whole water column, the pressure is negative. This is smaller than the atmospheric pressure. So pressure is negative. Although this is completely saturated, there is no air in it, but the pressure is negative, right? Similarly, above this groundwater, you will have a saturated zone where pressure will be negative. Above this partly saturated, you will have more negative pressure. So this is called something called suction, we call. This is lower than the atmospheric pressure. So this suction determines what is a strength, because some part of the suction actually translates to your shear strength, not all. If the more amount of suction doesn't mean that more amount of shear strength. Is not linearly correlated. I will discuss anyways in coming slides. So simple analogy, if you have a clay soil, this height could be as high as this much, or the pressure could be as high as 30 megapascal. This is suction. and negative pressure that exists in soils could be 30 megapascals. In fact, we can determine in the laboratory. We can control this suction also. To understand this, the suction values and shear strength or hydraulic characteristics during the rainfall events, so that we can understand how the factor of safety is vary with time, because that is what is required in the predictions. The important constitutive relationship is this: the relation between matrix suction and volumetric water content. So the matrix suction just now I have described, which is actually a lower pressure or negative water pressure over and above the less than the atmospheric pressure. That is on the x-axis, and on the y-axis you have volumetric water content, volume of water, the total volume. So different stages, this is how the suction is changing, and this is how the water held in the pore space is actually getting changed. So from this, it is very easy to actually correlate and derive the hydraulic conductivity function, because this determines how much amount of water actually percolates into the ground. So eventually, using the soil water characteristic curve and hydraulic conductivity function, which is a relationship between suction as well as the hydraulic conductivity, so we can solve expressions like this. This is called Richard's expression in 3 dimension, to determine what is the variation of suction or volumetric water content with space, in 3-dimensional space in the slope, so that we understand what is the shear strength that is actually changing with time, so that when we are doing slope stability analysis by simply discretization or simply by considering the individual slices using limit equilibrium technique, so it is possible to construct the force polygon, and then by considering the partly saturated conditions and the shear strength which is actually coming, and we can predict what is a factor of, we can determine what is a factor of safety. Now, so how it works? First of all, for example, you have a slope something like this. So where you have a lot of instrumentation here, extensiometers and tilt sensors and other things can be placed. Similarly, the suction and moisture sensors are very commonly placed something like this. And using the suction or moisture, which are determined at real time, so are used to predict the factor of safety. How do we do? Simple. When the suction or moisture contents are determined in real time, so we know that how the suction or moisture content is changing within this whole slope at different elements. So using this, now you can determine how the shear strength is actually changing, because we know the first of all relationship between moisture content and suction. From their hydraulic characteristics can be determined. Using that, you can determine what is the amount of water that is actually going to get in given time into deeper than this, because you are only getting discrete points of data. Continuous data you can only get using Richard's expression and understanding how the flow behavior is actually taking place. Then after that, you can construct the shear strength values, shear strength behavior. Now, if you feed into limit equilibrium technique or limit analysis, it can provide you the factor of safety. Limit analysis, there is a different approach to determine the factor of safety, reduction method, but limit equilibrium method, direct approach to determine the factor of safety. If this factor of safety, by considering number of slip lanes, is actually becoming close to 1, that means the that the landslide is eventually going to occur. So that is how the landslide prediction is generally done. Now, one particular issue here. So when generally the suction sensors are placed, this is very commonly done. So sometimes what they do, they establish the soil water characteristic curve as well, because that is required for the hydraulic characteristics and shear strength characteristics. What it is generally done is by placing these sensors in a compacted soil, compaction density is as close as possible to the field conditions, and completely flooding the soil, and then continuously monitoring. With time, they monitor what is the change in the suction, what is the change in the moisture content. This is MPS sensor, which can provide you very high suctions. And this is a moisture sensor, 5TM sensor, which can provide very precise values of volumetric water content. So there are several works where they were determining in real time what is the change in the moisture content as well as the suction in soil due to this change in the water content within the soil due to flooding. So this is exactly the same thing is happening if you are monitoring the suction values or moisture content in the actual scenario, actual slopes, right? So, but then what happens is that you are accumulating a huge error because you're not giving ample time for the sensor to properly respond, because there is something called response time for these sensors. If you take even tensiometer or MPS sensor, any other thing, they require ample time for to respond or come to equilibrium with the outside matrix. But before it responds to that, outside environment is actually getting changed because rainfall infiltration is taking place. So it is not able to get the suction values correctly. So for example, if I do the same experiment, simple experiment, where I've inserted the sensors and flooded or ponded the soil with water. Now, the moisture content versus suction value is this. This is the soil water characteristic of what I'm obtaining. But on the other hand, I can do something else. I allow only small moisture to get in. And so the water content is somewhere here. And now I'll close the wall. I'll wait for equilibrium to achieve. Now I'll only consider the equilibrium values of suction and moisture content, right? So initially soil is dry. So that means somewhere here. And then I allow small moisture to get in. So when small moisture is actually getting in, this eventually gets in, this gets saturated. Above this, small moisture get in because of capillary action. Because I was showing some capillaries and there is a raise in the water level. Soil pores behave like capillaries, number of capillaries with different sizes. So moisture gets in. Thin capillary, more amount of water or highest level. So therefore, different at any given suction, at any given section, cross section, you may have different levels of waters. So overall, you will get particular water content. So that is only one point. Then I allow some more water to get in. So I'll get another point. So I'm here waiting for equilibrium to take place. So this is the equilibrium path, right? So this way, if I determine, you can see the difference between equilibrium paths and the immediately without waiting for equilibrium to take place, what we are getting. This is a commonly done in field as well as in the laboratory. For establishing SWCs in the laboratory, for measuring the suction values in the field during the rainfall events. So this is the error we are accumulating. Even you use simple sand, even loose state and dense state. So the time that is taking is large, sometimes even 15 days using sand for come to equilibrium at certain water contents. So imagine natural soils, because natural soils are not sands, right? Until, unless until you have a sandstone and which is actually becoming a soil because of some weathering process, and then which is actually is contributing to certain suction or something. But otherwise you have laterites and other soils, which will take enormous time for establishing the equilibrium to take place. So therefore, using the suction sensor, if you are establishing something, you are actually accumulating a lot of error. And equilibrium one definitely takes a large amount of time. You require a huge time to establish this one soil water characteristic code data. I'll not spend more time here because I think I already spent 40 minutes here. And you have other methods, because often this is not that easy, because when the densities are changing, when the soil patterns are changing, it takes enormous time. But we have other methods like multi-step outflow technique, and they also have certain limitations. And in fact, we have tested a number of these methods for establishing the soil water characteristic, starting from sands to laterites to micaceous soils to even bentonates, like for nuclear waste repositories or something. Anyway, so we have tested a number of things. This is osmotic technique and vapor equilibrium technique. Using that also we could establish very good soil water characteristic curve and comparable to the other techniques, what we are currently using, right? So in the monitoring, next time we should not use suction sensors because they are erroneous. Only moisture sensors should be used for determining the moisture content variations, plus combinedly with the laboratory determined soil water characteristic curve to determine the suction, so that we can read what is the hydraulic conductivity changes and also what is the change in the shear strength. So shear strength, which actually is increased, shear strength is more in partly saturated conditions because of the presence of surface tension force additionally, or capillary forces. Capillary forces, sometimes if you have clays, then electroosmotic forces or electrostatic forces also would contribute to the shear strength of the soils. So we generally use suction controlled, triaxial test, suction controlled direct shear box test, because we should not use the routine direct shear box test for partly saturated conditions or triaxial systems, because it has a lot of limitations. The cavitation and other issues are there. So the existing systems like the suction control also cannot provide the complete information of shear strength variation with suction as well as water patterns. So we have number of these techniques for establishing shear strength directly from soil water characteristic curve. So mostly whatever we have currently, the analysis like Bishop, Fredland, or Liu and Lycos, very recent, using suction stress concept, they provide similar results for establishing the shear strength or effective stresses in this case. So this is how the shear strength changes with suction. And if you look at the trend, this is not linear, right? As suction increases, shear strength should not increase. Essentially, the fully dry state or fully saturated state, the shear strength should be same. It should not be different. So somewhere in between, maximum shear strength will be achieved. As saturation takes place, so towards the left when it is moving, it will drop. So this is where the failure takes place. Somewhere in between, the failure takes place. So using these concepts, physics-based models, there are several models like using steady-state models, because the analytical models could be developed using steady-state models directly to estimate the factor of safeties, which are very handy, but they compromise on certain aspects, like they use only steady-state flow, not the transient flows. But steady-state flow is not very common in the field conditions, because boundary should be constant. Boundary should not vary for steady state to actually happen. So there are some transient states, but here also there are certain limitations using certain soil water characteristic data, and also certain limitations in the using the certain models for hydraulic conductivity functions. So these are some of those models. I will not go details of these particular things. Definitely you will get these things if you look for. I have given the citations, Srivastava et al., and which are used in Liu and Lycos and other models. Essentially, they have to compromise on the sliding surface, which is not the realistic surface. This is a infinite failure mechanism they have shown, and that is how they predict the factor of safeties. But the numerical models provide useful information, because the slip surface can be of your choice, and more information can be provided, like the layering effects and everything can be brought into, and also you can use different models for predicting the landslide events or determining the factor of safeties. This is one of the case study which we have taken from NEHU, Northeast Hill University from Shillong, Meghalaya. So where we got the contour maps and we actually analyzed the slope stabilities. Our major objective is to predict the landslide event when it exactly occurred. This is kind of a back analysis. Already the slope has failed on particular days, something like June 27th or something in 2019. What we are trying to do is, using the existing data, whether we can predict the landslide event or not using the back analysis. That's what we are trying to do. So we took the antecedent rainfall event for about a year, and then critical rainfall event for about month or more than a month. And now using the antecedent rainfall events, we have created here. So we have actually observed the burst water table, and then what is the variations in the suction and then moisture content within the slopes. And during the critical rainfall event, we actually got the factor of safety variations. So this is how the factor of safety varied using this method I have proposed, with what we have mentioned. There is equilibrium approach for the soil water characteristic prediction. If you use a transient method, it will fail on the first day itself. But here it exactly fails. It matches very well Exactly on 27th June, it fails. And in fact, the amount of mass that has slided also exactly matches. So this is how we could predict the already occurred landslide using all the parameters, because generally we get the data only once the failure has occurred. Before that, it is very rare that someone asks us to monitor and then predict whether landslide occur or not. Okay. So the factor of safety variations, etc., I was showing here, and using equilibrium method and transient methods, and some parametric analysis I was providing. Can I take 5 more minutes? I think I've already finished 45 minutes. And some parametric studies I was actually presenting here with and vegetation, how the factor of safety changes in this particular case. And until then, I was very hoping that we could predict any given landslide event if we know all these data. But then my confidence levels have completely gone down after seeing this particular landslide event. This happened last year, June 30th, in Manipur, in Tupul Yard. This is Ijai River, which is flowing here. And from Ijai River, the ridge of this particular slope is about 1 kilometer, more than 1,000 meters. And at about 300 meters level or 400 meters level, they were actually making one yard, railway yard. And there are tunnels here, and this side also tunnels are there. And rail comes out of the tunnel. Tunnels aren't functioning; they're already there. So train comes out of this tunnel and then comes to this particular yard, and again it enters into the tunnel. So this was the actual plan. So tunnels were ready. Tunnels were already ready, and they were making the yard ready. And here the benching work was actually taking place. And initially benching was actually taking place here. And if you see, look at the rock mass here. This particular rock is mostly shales and conglomerates, mostly shales, bedded shales. So bedding is actually shown here. And some parts it's purely weathered, and it appears like a laterite soil is actually coming out red in color. And some places this is a little fresh. And this is how the geology of the land and where the benching was actually taking place. And it seems there was a huge sound that heard for continuous 2 days, but then somehow this particular indication was ignored. And on June 30th, there was a huge mass actually came down, and 71 officers have died in this particular landslide, June 30th. And I visited in the month of September, and I was actually standing on a heap. I was told that 30-40 bodies are not even recovered, and they are under the this particular heap where I was standing. And the interesting, I mean, very moving part is that generally the landslides are shallow. The rainfall-induced landslides are very, very shallow, hardly 2 meters. Beyond that, the failure zone doesn't exist. But in this case, the failure occurred 60-meter deep, the failure surface. If you think that you will place some sensors and then monitor, that is not possible, because generally your moisture readings or suction readings take place from shallow depth, hardly 1 meter, 2 meter, but 60-meter deep failure that has occurred. And what I have learned here is that there were several earthquakes that happened not immediately, but several years before. And actually there are several fault zones. So the geology has not been studied well during that particular time. And the triggering this fault zone actually triggered the landslide from that particular point. And that is the reason why 60-meter deep failure surface was existing in this particular case. In this very unfortunate incident. And now some measures are currently have been taken. And in this particular scenario, the prediction is not possible using the physics-based models, because first of all, detection is not possible. I have actually gone up to the ridge, went up to a certain distance by vehicle, and after that I walked up. But from ridge, because initially some speculation that there was some kind of a cultivation that is taking place, possibly because of that the failure has occurred or something else, but that was not the case. But the actual failure, I think, was because of the pre-earthquake scenarios, which created a fault zone and a lot of accumulation of pore pressure or pore water during the subsequent rainfall events, and slowly this has actually triggered and whole mass actually slide down. And in this particular scenario, beforehand prediction is very, very difficult using physics, normal methods by putting sensors or something. So possibly the satellite-based techniques would be helpful, I thought, because we just entered after this particular event, that satellite-based techniques would be helpful in understanding this movement beforehand. Because if I go quickly, we have in the visible range, you have optical remote sensing data and thermal remote sensing and microwave. So optical, I have shown in one of the case offline, where NESAC has provided the optical sensing images. But then mostly when the atmosphere is cloudy, it is not possible to get these images. And microwave sensing data, which provides a useful data for detecting the movements that takes place. So these are some of the satellites currently available, and we rely on the Sentinel data for microwave, Sentinel-2, and SAR data or INSAR data, which provides SAR image, which consists of amplitude and phase. Based on the relative change in these things, we can detect what is the movement that is actually taking place. And for this is the INSAR analysis for the Tupul, Manipur landslide. And unfortunately, we could not get very useful results because hardly 50 mm displacement that was noticed before the landslide and after the landslide event, because there are more and more limitations with these techniques as well. Like when a lot of vegetation was present, it is very difficult to actually get these things. And for this particular scale of 1 kilometer high and then 60 centimeter width, etc., there is not possible to detect accurate changes in the slope, because resolution is not that accurate, not good for this particular scenario. But because for the susceptibility maps, it is fine, satellite data. But for this particular case, it is not that useful. Moreover, when the satellite moves towards the north, this out of sight becomes, because any slope which is actually facing towards the north, that is not possible to detect. So because of that, we could not get some of the data in Aflong and other regions. So these are some of the limitations currently we have in prediction of such landslide events. So these are some of the takeaway points I actually summarized from my presentation. One thing is suction sensors should not be used for landslide monitoring and for the subsequently the prediction of these things, because suction sensors have huge response time. Sometimes it in days, several days, for one particular moisture content to achieve, because generally the rainfall event hardly lasts for a few days or sometimes less than a day. So then by that time, what suction sensor can give is all erotic results. So it should be moisture sensor combined by lab measured soil water characteristic curve for analyzing the factor of safety variations with time. Either the use of general physics-based models or application of satellite data is challenging for large landslide events, what I mentioned in the Tupul landslide in Manipur. So in this particular scenario, I think detailed geological map of the region, so with the human intervention, might help in understanding the landslide susceptibility in general overall, and also from this susceptibility map, one particular region, more rigorous detailed geological map if we develop, where there are we can detect the faults and other things, and we can understand how the moisture is actually getting accumulated from the satellite data or something, and that could possibly help. So this is the workforce or my support for my whatever little understanding I have in this area or any other areas. My research group, this is a research group I have, and my past and present students, and these are some of the groups who have supported me for with the research grants and also from providing the data for the consultancy works, etc. With this, I thank you. I don't know how much I could bring the audience attention, because this is the last lecture. With this, I thank you so much. I can take any questions if you have.
Yeah, sure. Thank you very much, because as you mentioned, the last one of the presentation is somehow always the most difficult. But let's see if we have some questions from the public. In the meanwhile, my compliments for your presentation, your very comprehensive work. I think we have a question from the chat. No.
Oh, yeah. Yes, I have one question.
Okay, sorry. Yes, from the chat there was another compliment. I think we have a question from Simone Donati. Is that right?
Right.
Yeah. Okay. Please go ahead.
I'd like to know what's the method to choose the position of the moisture sensor on the landslide. Is there some kind of rule or technical constraint for them?
So generally, these sensors cannot go very deep because they have their own limitations. Because the data acquisition may not be possible if it is very deep. Generally, they are confined to 1-2 meters deep, and then rest of the data we derive from the models, like Richard's expression, what I was mentioning. So these are the discrete points you are getting from by placing them, and it is generally the maybe the thumb rule or whatever it is that you place depending on the region. You go at different depths, say 0.5 meter and 1 meter, and different points along the slope, and this would give a sense of how the suction and moisture is changing. Beyond that, actually, you are detecting these variations using the Richard's expression, theoretical expression, because completely it is not possible to detect how the moistures are, things are changing.
Thank you.
Thank you for your question.
Sir, good evening.
Yeah.
Good evening.
Sir, it is a very interesting. It is an application of unsaturated soil mechanics for rainfall-induced landslide. Sir, what is your advice regarding that use of some kind of capillary barrier at the top of the slope, which may restrict the flow of ingress of water to the soil mass, so that soil mass can remain unsaturated or in dry, close to its dry state, and maintain its shear strength, which may restrict the instability of the slope. What is your opinion on that?
Yeah, these are one of the measures. I did not talk in this particular presentation, but this capillary barrier mechanism is one of that which I've been working on since my initial days in IIT Guwahati. 2012, I had a project on capillary barrier mechanism, and for the slopes also we have used. But the major problem is when these, for example, you put a capillary barrier just by spraying or something, right? Not detailed manner you are constructing something, because that is not possible. Over a stretch of 35 kilometers, you cannot provide a silt or any other layer over a huge stretch. But spraying is possible. Some grouting or something people often do, but using other slurries we were actually trying, but they also wash away with time, right? They are fine. Okay. I mean, for few rainfall events, but repeated intervention is required for maintaining lower hydraulic conductivities for that.
Okay. That means
Yeah.
That means, sir, we need to do adequate subsurface drainage.
Yes.
But it's, to keep the slope in unsaturated or dry condition, not to make it saturated one, so that factor of safety goes down and become unstable. Is it not?
Of course, there are some bioengineered measures.
Yeah. Nowadays, bioengineering measures are also coming being implemented.
The water content is actually maintained lower.
Yeah. Okay. Thank you, sir. Thank you.
Yeah, thank you. In fact, you were saying about unsaturated. I have in fact course on offered for.
I did it, sir. I did it on NPTEL. Yeah, it was a very fantastic and quite comprehensive one. I did it for my enrichment of knowledge, because that unsaturated soil mechanics is usually not covered.
Yes.
It is a emerging
so that is
field
available for free of cost. On one of the
even I appeared for the examination for certification also.
Very nice.
And he provided the Lou and Lucas books for our own study, Professor Rahajo, and all these books and theories I can remember. I have met with you in ISC Bangalore conference. I can remember you, sir. Thank you.
Oh, very nice. Yeah, thank you.
Okay, thank you again, Dr. Bharat, for this nice presentation. Very interesting. And with that, I think we can move to the conclusions of these workshops. But first,
I got only one small clarification.
Oh, one more question. Yes, you're welcome.
Yeah, Professor Bharat, I think perhaps as of now, I've been going through a lot of papers. But I don't think anybody had applied unsaturated soil principles of unsaturated soil mechanics to, in depth for the either slope stability or landslide analysis or anything like that. Probably your effort is more a pioneering effort. That's what I feel. Maybe if I'm wrong, I stand corrected. Am I right?
You are right, actually. Thank you so much. And yeah, we've been trying hard to, give more focus on the soil physics and soil chemistry and understand how it behaves during this particular rainfall events, etc. And then try to, come up with some measures.
Yeah, but instrumentation is more important. See,
instrumentation is important. Yes.
Let me be very honest with you. This is the first time I'm attending this topic because my area is for deep foundation and pile group analysis, and I'm from a contracting company. I've been a designer, right? I became a researcher off late in the last 10 years after my retirement. But then what I'm now looking at it is a lot of field monitoring is required if you go further on top of this topic. There's one side on prediction is involved, and the other side forensic study also is involved. Unless you collect the data from the landslide that have occurred and then try to apply the derive the principles and then go about based on the various soil profile and the properties of the soil and then the movement, right? Moisture movement. Yeah. So I think so. You are trying to getting into the unsaturated soil mechanics part is really very interesting.
But still, sir, we have certain difficulties. You correctly actually brought out the right point. But actually still certain difficulties, especially when you have soil and rock mixed up. How to evaluate this particular thing is a little challenging still in a laboratory scale.
Yeah.
Right? So still we are looking at these aspects, and definitely your field observations and experience also would help in understanding these things. Yeah, thank you, Dr. Balkumar.
Yeah. So the data collection is more important. I remember my first overseas trip for a conference was to Oslo, where we had a 2-3-day conference on field measurements in geomechanics. This was the conference title. And there were 3 papers on landslide. I remember that now. In fact, the proceedings is there now. Maybe in the night I will have to take that and see what it talks about at that time. Right?
Yeah, perfect. Yeah.
The papers are from, if I'm not mistaken, it is from Italy. I remember that because I met those people, and that was beginning of my research career. Where correct, but it's really very interesting, Dr. Bharat.
Thank you. Thank you so much. Yeah.
Any other question? Okay, so let me thank once again everyone, all those who help organizing this workshop from Italy and from India. All the speakers of yesterday and of today, and of course all the attendees. You were very numerous, with active participation, with a lot of interesting questions, which gave birth to a fruitful discussion, I think. And with that, I leave the floor to Nilima. Are you there?
Good evening, good afternoon to everyone. First of all, I thank all the speakers. We had excellent presentations from different aspects of landslide, considering starting from forecasting, monitoring, case studies from the industry and unsaturated part. And Bharat, it was an excellent presentation. And thank you so much. And it was like continuous 5 hours. Participants were actively participating and asking questions. So thanks to everybody, and thanks to my student also, Kunal, who helped me in organizing this event, and also my counterpart, Dr. Shamul. Without this, it could not have happened. So as a concluding session, I have a couple of announcements I can say. So all the lectures are recorded and it will be uploaded, and for Italian participants, I can share the details with Dr. Shamul, and I'll share those details with our participants from the Indian side, because I do have the registered participant details. You can, and also I would like to give all the speakers the email IDs in that, so you can contact from both the sides. You can contact them in future for any sort of discussions or in collaborations. I also thank my sponsors for giving excellent presentations and also voluntarily supporting. So it was a great event, and thanks everyone. So with that, good evening and good afternoon. So we are officially closing, Dr. Samuel, right?
Yeah, I think we are
sure.
done. Yeah.
So thank you so much. Thanks, everyone.
Thanks, everyone. Goodbye.
Bye.